Right now, without knowing it, you are drifting through one of the emptiest regions of the entire observable universe. Not a small gap, not a quiet neighborhood between galaxy clusters. A hole in the cosmic fabric roughly 2 billion light-years wide, with our galaxy sitting somewhere near its center. This isn't a poetic metaphor. It is a measured, mapped, scientifically documented feature of the cosmos we inhabit. And for most of human history, including most of the history of modern cosmology, nobody knew. In 2013, 3 astronomers named Ryan Keenan, Amy Barger, and Lennox Cowie were engaged in something that sounds deceptively routine, mapping the distribution of galaxies across billions of light-years. They cataloged 35,000 galaxies, checked their distances using redshift measurements, and compared the observed density of matter near Earth to what cosmological models predict. The numbers did not match. Everywhere they looked, within roughly 1 billion light-years in every direction, galaxies were sparse, not slightly sparse, about 20% fewer galaxies than the cosmic average. The underdensity stretched outward uniformly in all directions, forming a sphere of cosmic emptiness with the Milky Way sitting uncomfortably close to the center. They named it the KBC void, using their own initials. The name sounds almost casual. The implications are anything but. To understand why this discovery matters so deeply, you need to understand what a cosmic void actually is, and why the universe produces them at all. The universe is not a smooth, uniform soup of evenly distributed galaxies. At the very largest scales, it resembles something closer to a sponge or a foam, with enormous bubbles of near emptiness surrounded by thin walls and long filaments where galaxies cluster together. This architecture is called the cosmic web. It is the largest structure in nature. When astronomers say a region is a void, they mean the density of matter there is dramatically below average. The KBC void contains roughly 15% of the typical cosmic matter density. If a representative region of the universe holds 10 galaxies within a given volume, that same volume inside our void might contain only 1 or 2. Between those lonely, scattered galaxies stretches space filled almost entirely with dark matter, dark energy, and the occasional wisp of neutral hydrogen gas. Gravity barely operates here. Without sufficient mass to pull structures together, galaxy formation slows to a crawl. The void remains a void. This emptiness has a cascade of consequences that reach far beyond aesthetics or scale. Gravity is already the weakest of the 4 fundamental forces, requiring enormous concentrations of mass to produce noticeable effects. In regions where matter is this sparse, gravity essentially loses its grip on the environment. What takes over is dark energy, the poorly understood pressure that drives the accelerating expansion of space itself. In dense regions crammed with galaxies and clusters, gravity and dark energy wage a constant tug-of-war, with gravity slowing the outward push of expansion. Inside voids, gravity has so little mass to work with that dark energy wins decisively and almost immediately. The result is that voids expand faster than the rest of the universe. They grow like bubbles, inflating from within, their boundaries pushing outward into the surrounding filaments and walls of matter. Scientists confirm this by measuring how galaxies near the edges of voids move compared to galaxies in denser filaments. The void galaxies are rushing outward, away from the void's center, faster than cosmic expansion alone would explain. Something extra is pushing them. The gravitational pull from the dense matter outside the void is, counterintuitively, causing galaxies within it to fall outward toward those denser regions. Think of it as a gravitational valley surrounded by mountains. In a landscape, you would fall toward the valley. In space, where the relevant gradient is density rather than elevation, galaxies fall outward toward the mountains of matter that surround them. Our own galaxy is already doing exactly this. The Milky Way is moving away from the local void at roughly 600,000 miles per hour, driven by the gravitational imbalance between our underdense environment and the denser structures beyond it. This physics shows up in one of the most reliable maps of the early universe. When scientists study the cosmic microwave background radiation, the faint thermal afterglow of the Big Bang that fills the sky in every direction, they notice that light passing through cosmic voids appears slightly cooler than average. Photons traveling through an underdense region lose a small amount of energy through a process called the integrated Sachs-Wolf effect. The reduced gravity inside the void allows the photon to lose more energy climbing out than it gained falling in. This shows up as slightly cooler patches on temperature maps of the microwave background. These cold patches align precisely with where independent galaxy surveys detect large voids. The alignment is not coincidence. It is the same physics, showing up in two completely independent measurements. To understand why the cosmic web exists at all, and why voids are so common, you have to go back to the very beginning of everything. Immediately after the Big Bang, the universe was not perfectly uniform. During a phase called inflation, an exponential expansion in the universe's first tiny fraction of a second, quantum fluctuations were stretched from subatomic scales to cosmic scales. These fluctuations created minuscule variations in matter and energy density across the early universe. Some regions were slightly denser than average. Others were slightly less dense. The differences were extraordinarily small, roughly 1 part in 100,000. But gravity amplifies even the tiniest advantages. Regions that were even slightly denser began pulling in matter from their surroundings. As they grew denser, they became even more effective at attracting matter, creating a runaway feedback loop. Over hundreds of millions of years, these overdense regions collapsed into the first stars, then the first galaxies, then galaxy clusters, and eventually the long filaments and intersecting nodes we observe today. Meanwhile, regions that started slightly below average density lost matter to their denser neighbors. As matter drained away, those regions became emptier still. The underdense regions evolved into voids. Over billions of years of cosmic history, the initial quantum fluctuations have been amplified into the vast, sponge-like structure of the universe we inhabit today. The cosmic microwave background preserves a snapshot of those initial fluctuations when the universe was only 380,000 years old. Satellites have mapped temperature variations across the entire sky, with warmer spots corresponding to regions of slightly higher density and cooler spots to regions of slightly lower density. Scientists can take that pattern and run it forward through computer simulations to predict how structure should develop over billions of years. Those simulations reliably produce a cosmic web of filaments, clusters, and voids that closely resembles what galaxy surveys observe. The match between theory and observation is one of the greatest triumphs of modern cosmology. However, there is a problem. The simulations rarely produce voids as large or as deep as the KBC void. Some analyses have estimated that a void of its size and density deficit represents roughly a 10 sigma statistical deviation from expected values under standard cosmological models. To put that in context, a 5 sigma result means there is less than a 1 in a million chance the event occurred by random chance. A 10 sigma result is almost incomprehensibly improbable. You would need to survey trillions of universe-size volumes before you would statistically expect to find even one structure this extreme. Yet we live in one. This statistical tension has not been resolved, and it drives much of the ongoing debate about the KBC void. Some cosmologists accept the result at face value and conclude that our location is genuinely unusual, a cosmic rarity. Others question the measurements, arguing that the void's depth and size may be overestimated. Still others have proposed that the tension points to something wrong with our cosmological models themselves, perhaps with the theory of gravity or the assumed properties of dark energy. Each of these positions has serious scientific arguments in its favor, and none has yet been definitively ruled out. The scientific picture becomes dramatically more significant when you consider a persistent and increasingly urgent discrepancy in modern cosmology known as the Hubble tension. The Hubble constant is the number that tells us how fast the universe is expanding. Specifically, how many kilometers per second faster a galaxy appears to recede for every additional megaparsec of distance between us and that galaxy. For decades, cosmologists have used two completely independent methods to measure this number, and those methods consistently disagree. The first method examines the cosmic microwave background. Scientists measure the subtle temperature fluctuations in that ancient light, feed the data into cosmological models that describe the very early universe, and then calculate what the expansion rate should be today, based on how the universe has evolved over 13.8 billion years. This method produces a Hubble constant of approximately 67 kilometers per second per megaparsec. The second method works locally. Astronomers identify objects with known intrinsic brightness, primarily a class of exploding stars called Type Ia supernovae, and a class of regularly pulsating stars called Cepheid variables. Because the physics of these objects is well understood, their true brightness can be calculated independently of distance. By comparing how bright they appear to how bright they actually are, astronomers can calculate exactly how far away they are. Combining distances with observed redshifts gives the local expansion rate directly. This method consistently produces a Hubble constant of approximately 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are extraordinarily precise, with very small error margins. In a well-functioning theory of cosmology, both measurements should agree because they are measuring the same underlying physical quantity. They do not agree. The discrepancy has reached 5 sigma statistical significance, meaning the chance of it arising from random measurement error is less than 1 in a million. Something is wrong, but cosmologists are not yet certain what. The KBC void offers a compelling explanation. When astronomers use local supernovae and Cepheid stars to measure the expansion rate, they are making measurements within the void. The void's low matter density means there is less gravitational pull resisting the outward motion of galaxies. On top of that, the dense matter outside the void is gravitationally pulling galaxies within it outward toward the void's boundaries, adding extra velocity on top of ordinary cosmic expansion. Galaxies inside the void appear to recede slightly faster than they would in a typical region of the cosmos. The measured local expansion rate appears inflated because it is inflated, not by new physics, but by the unusual geometry of our local environment. When cosmologists model how a void with the KBC void's size and depth would affect local expansion measurements, they find it could boost the apparent rate by approximately the amount observed. The Hubble tension might not require new fundamental physics at all. It might simply require acknowledging that we are measuring the universe from inside a cosmic hole. The cosmic microwave background measurement is unaffected by this problem because it probes the early universe, long before voids of this scale even formed. The structure that creates the KBC void coalesced over billions of years of gravitational evolution. When the microwave background photons were released, 380,000 years after the Big Bang, the universe was still nearly smooth. That measurement samples the universe's global expansion properties without any local distortion. The local measurement, on the other hand, is contaminated by our unusual position. If this interpretation is correct, it carries another significant implication. For our estimate of the universe's age, the current standard estimate places the age at 13.8 billion years, derived primarily from microwave background data. But many reports about dark energy and the accelerating universe lean heavily on local expansion measurements. If those measurements are inflated by roughly 9% due to void effects, then the local expansion rate is not the universe's true expansion rate. The microwave background estimate is more reliable for the universe's global properties. The concern becomes acute when you consider stellar ages. The oldest stars in globular clusters, ancient gravitationally bound groups of hundreds of thousands of stars, appear to be approximately 13 billion years old, based on stellar evolution theory. Astronomers determine this by observing which stars in a cluster have exhausted their nuclear fuel and died. The most massive remaining stars in the oldest clusters are just barely still alive, which, combined with our detailed understanding of how quickly stars of different masses burn through their fuel, indicates those clusters formed about 13 billion years ago. Space missions like Gaia have refined these measurements by providing precise distances to globular clusters through parallax. The revised measurements confirm the oldest clusters are very close to 13 billion years old. If the local expansion rate were taken as the true rate for the entire universe, the implied age would be closer to 12.7 billion years. Stars cannot be older than the universe. The void hypothesis resolves this tension elegantly. The true expansion rate is the lower value suggested by the microwave background. The universe is approximately 13.8 billion years old, and the local measurement is inflated by our unusual position. No stars are required to predate the cosmos they inhabit. Beyond the expansion rate and age discrepancy, the KBC void also explains something called peculiar velocity flows, the systematic bulk motions of galaxies that standard cosmology struggles to account for. In the standard model, peculiar velocities of galaxies should average out and become negligibly small when measured over volumes a few 100 million light-years across. The gravitational pulls from structure in every direction should largely cancel. Observations tell a different story. Surveys measuring galaxy velocities to distances of 200 to 300 million light-years find bulk flows reaching 400 kilometers per second or more, several times larger than standard models predict. These flows are not random. Galaxies across enormous volumes are all moving coherently in roughly the same direction, which implies the presence of large-scale structure, creating a systematic gravitational gradient. The KBC void is precisely the kind of structure that would generate such flows. Matter within the void is accelerating outward toward the denser filaments and walls at the void's edges. The Cosmic Flows Project has produced the most detailed maps of these velocity patterns to date, and the observed bulk flows match closely with predictions from models that incorporate the KBC void. One of the most useful tools for independently verifying the void's existence and quantifying its properties comes from a phenomenon called baryon acoustic oscillations. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma in which ordinary matter and radiation were tightly coupled together. Pressure waves, essentially sound waves, propagated through this plasma, creating oscillating compressions and rarefactions in the matter distribution. When the universe cooled enough for atoms to form, matter and radiation decoupled. The sound waves froze in place, imprinting a characteristic scale on the distribution of matter. That scale, roughly 490 million light-years, acts as a standard ruler embedded in the clustering of galaxies. Because the physics that produced it is well understood, astronomers can measure its apparent size at different cosmic distances to trace how the universe has expanded over time. When scientists analyze galaxy clustering in our local region using this technique and compare it to what distant measurements predict, they find a clear deficit in our neighborhood. The characteristic clustering scale appears subtly different from what far-field measurements suggest, consistent with our region containing less changed matter than average. The baryon acoustic oscillation measurements provide independent confirmation that the void exists and allow its depth and extent to be quantified with precision. The Dark Energy Spectroscopic Instrument, which began operations in 2021, is mapping tens of millions of galaxies with extraordinary accuracy. Within the next few years, astronomers will have characterized the void's properties to within a few % uncertainty. Our local cosmic address has additional layers worth understanding. The Milky Way belongs to the local group, a collection of roughly 80 galaxies, including our much larger neighbor, Andromeda. The local group sits within a larger structure called the Laniakea supercluster, a gravitationally bound complex containing roughly 100,000 galaxies spread across 520 million light-years. Here is the paradox. Laniakea, despite containing 100,000 galaxies, resides entirely within the KBC void. How can an enormous supercluster exist inside an underdense region? The answer lies in scale. The KBC void is underdense when measured over very large scales, billions of light-years across, but it is not uniformly empty. It contains local concentrations of matter, including Laniakea, that are denser than their immediate surroundings. The underdensity is a large-scale statistical property, not a guarantee of perfect uniformity throughout. Laniakea is a relatively dense node within a fundamentally underdense ocean. Adjacent to our position sits another underdense region, called the local void, extending about 200 million light-years. Our galaxy is moving away from the local void at roughly 600,000 miles per hour, driven by the gravitational pull from denser structures farther away. These nested structures, a small local void beside us, a supercluster around us, and a vast megavoid encompassing all of it, together define the cosmological context from which all of our measurements of the universe are made. This raises one of the deepest conceptual challenges in modern cosmology. For centuries, science has progressively stripped Earth of any special cosmic position. Copernicus established that Earth is not the center of the solar system. Later observations showed the solar system is not the center of the Milky Way. The Milky Way is not the center of any larger structure. The cosmological principle, one of the foundational assumptions of modern cosmology, is the ultimate expression of this progression. It states that, on sufficiently large scales, the universe is homogeneous, meaning the same everywhere, and isotropic, meaning the same in all directions. No location is cosmologically special. The KBC void threatens this principle at a fundamental level. If the void is 2 billion light-years across with a 20% density deficit, that represents a significant inhomogeneity on scales where homogeneity is supposed to hold. And we happen to sit near the center of this anomalous structure. That is not what the cosmological principle predicts. Some cosmologists respond that the principle is only expected to hold on scales somewhat larger than the void, so the void is not a true violation. Others calculate that, even accounting for expected statistical variance, a void this large and this deep is so improbable under standard cosmology that it should give us pause. Whether the cosmological principle survives in its current form may depend significantly on how well we measure and understand this structure over the coming decade. The existence of a void this extreme has led some researchers to revisit the theory of gravity itself. Einstein's general relativity, published in 1915, has passed every experimental test for over a century with extraordinary precision. But if the KBC void is genuinely too large and too deep to arise naturally in standard simulations, perhaps gravity does not behave exactly as general relativity predicts on the very largest scales. One prominent alternative, called modified Newtonian dynamics, or MOND, proposed in 1983, suggests that gravity behaves differently when accelerations are extremely small, as they are on the outskirts of galaxies, and on cosmological scales. Under MOND, gravity becomes stronger than general relativity predicts in these low acceleration environments. Structure formation becomes more efficient. Computer simulations using MOND gravity naturally produce voids as large as the KBC void without requiring unusual initial conditions. The statistical improbability disappears. However, MOND faces serious challenges. It struggles to explain the detailed pattern of temperature fluctuations in the cosmic microwave background. It also cannot easily account for gravitational lensing observations, where massive galaxy clusters bend light from background objects by amounts that require more gravitational influence than visible matter alone can provide. Other modified gravity theories have been proposed that predict gravity behaves differently in low-density environments like voids, which would make large voids easier to form. Testing these theories requires precisely measuring how matter moves in voids versus dense regions and looking for deviations from general relativity's predictions. That work is ongoing. The KBC void is not the only supervoid that has attracted attention. The largest known underdense region in the observable universe is the Eridanus supervoid, located in the direction of the constellation Eridanus. It spans roughly 1.8 billion light-years, comparable in scale to the KBC void. What makes the Eridanus supervoid particularly compelling is how it was discovered. Astronomers did not find it initially by counting galaxies. They found it by noticing an unusually cold spot in the microwave background temperature map, roughly 10 degrees across on the sky, where the radiation is about 70 microkelvin cooler than surrounding regions. A cold spot this large and this cold is statistically unusual. It appears in only about 2% of computer-simulated universes, suggesting it is unlikely to be a random fluctuation from the early universe. When astronomers surveyed the galaxy distribution in that direction, they found a large, underdense region roughly aligned with the cold spot. Light from the microwave background passing through this void on its way to Earth loses energy through the Sachs-Wolf effect, showing up as a temperature deficit. Calculations show that a void of this size and depth can account for roughly half of the observed cold spot anomaly. If both the KBC void and the Eridanus supervoid are real and as extreme as measurements suggest, it raises the possibility that large supervoids are more common than standard cosmology predicts. Two supervoids might still be consistent with standard models if you allow for statistical variance, but finding 3 or 4 would become increasingly difficult to reconcile without modifying the underlying theory. Galaxies that happen to reside within cosmic voids are shaped profoundly by their environment. Unlike galaxies in dense clusters, which interact frequently with neighbors, collide, exchange gas, and trigger bursts of new stars, void galaxies evolve in near total isolation. This difference in environment produces measurable differences in their properties. Void galaxies tend to be smaller, dimmer, and less massive than their counterparts in filaments. Many are dwarf galaxies, barely massive enough to retain their gas against outward pressure from internal processes. Without the frequent mergers that drive rapid evolution in dense regions, void galaxies change more slowly and remain structurally simpler. Most are late-type spirals or irregulars, rather than the large ellipticals that dominate dense clusters, which form primarily through repeated mergers that scramble spiral structure. Paradoxically, the isolation of void galaxies makes them unusually gas-rich. In dense environments, gravitational interactions with neighboring galaxies can strip gas away or trigger star formation that burns through it. In voids, galaxies retain their neutral hydrogen for much longer. When star formation does ignite, driven by internal instabilities rather than external disturbances, there can be plenty of fuel available. This occasionally produces starburst galaxies, experiencing intense, short-lived episodes of rapid star formation within an environment that otherwise seems too quiet to generate them. The chemical composition of void galaxies also reflects their isolation. Stars forge heavy elements through nuclear fusion and scatter those elements into space when they die. Successive generations of stars incorporate these elements, gradually enriching the galaxy's chemical environment. Void galaxies, with their slower star formation histories and fewer stellar generations, tend to be more metal-poor than galaxies in denser regions. The difference is real but smaller than simple models predict, suggesting that chemical enrichment involves processes more complex than straightforward generational accumulation. These environmental differences matter for a question that extends far beyond astrophysics: the possibility of life elsewhere in the universe. The distribution of matter shapes where planets can form and where conditions are stable enough for life to arise and persist over billions of years. Void galaxies face certain disadvantages. Lower metal content means fewer rocky planets in early generations. Smaller galaxies produce fewer stars, creating fewer opportunities for planetary systems to develop. But void environments offer certain advantages as well. Dense galaxy clusters are violent places. Galaxies collide frequently. Close supernova explosions can bathe nearby planetary systems in lethal radiation. Active galactic nuclei, the luminous-powered cores of many cluster galaxies, pump enormous energy into their surroundings, potentially disrupting planet formation and destabilizing atmospheres. Void galaxies evolve in quiet isolation. Stars form at moderate paces. Planetary systems have billions of years to develop life without catastrophic interruptions from the outside. Whether void environments are net positive or net negative for life is genuinely unknown. But the question is not merely philosophical. If we eventually detect other technological civilizations and can determine their locations, we will learn whether intelligence arises uniformly throughout the cosmos or preferentially in certain environments. A sample size of one, our own civilization, is statistically useless for drawing conclusions, but a sample of dozens of civilizations could reveal patterns that tell us something profound about where life is most likely to take root. The question of our unusual location connects to a deeper philosophical puzzle about the nature of scientific observation. For centuries, scientists have worked from the assumption, often unstated, that Earth occupies a typical position in the cosmos. The cosmological principle formalized this assumption mathematically, but the KBC void challenges it in a way that has practical consequences for every measurement we make. Every telescope observation we conduct is filtered through our local environment. The expansion rate we measure is inflated by the void. The age of the universe we calculate depends on which expansion measurement we trust. The properties we infer for dark energy depend on how accurately our local measurements represent the universe's global behavior. The void is not a minor systematic error. It is a major feature of our cosmic context that potentially touches the foundations of modern cosmology. This situation echoes a recurring theme throughout the history of science. Researchers have repeatedly had to confront the question of how to distinguish universal laws from the accidents of local circumstance, how to separate the true signal of nature from the noise introduced by the observer's particular vantage point. We corrected for Earth's motion around the sun. We corrected for the sun's motion through the galaxy. The void asks us to correct for something vastly larger, the properties of a region 2 billion light-years across. The challenge is that we cannot simply step outside the void and measure it from a neutral vantage point. We are embedded within it. Everything we observe is passed through its filter. Disentangling our local environment from the universe's global properties requires careful comparison of measurements made at different distances, searching for the point where local void effects give way to the properties of the universe at large. The universe we inhabit has another temporal dimension worth considering. We do not just live in an unusual place. We exist at an unusual moment. The cosmic web, with its elaborate structure of filaments, walls, clusters, and voids, represents a particular phase of cosmic history. Billions of years in the past, the universe was denser and more uniform. Structure had barely begun to differentiate. The cosmic web as we know it did not exist. Billions of years in the future, dark energy will have driven the accelerating expansion of space to extremes that isolate structures from one another. Voids will have swallowed enormous fractions of the observable universe. Neighboring superclusters will have receded beyond each other's cosmic horizons, their light permanently redshifted into invisibility. We live in a window when the universe has developed enough structure to be scientifically rich, but has not yet been torn apart by accelerating expansion. The cosmic microwave background is still detectable. Distant galaxies are still visible. The expansion of space is still measurable through multiple independent techniques. A civilization arising in a void galaxy billions of years from now would have none of these advantages. The microwave background will have stretched to wavelengths too long to detect. Evidence of the Big Bang will have become inaccessible. No distant galaxies will be visible. Such a civilization would inhabit a universe that appears to consist of only their immediate local group, with nothing beyond. They might conclude they live in a static island universe surrounded by an infinite empty darkness, with no suspicion of the vaster cosmos beyond their horizon, and no way to discover their error. We are fortunate not just to live when and where we do, but to live when the universe is still comprehensible. The void may bias our measurements, but at least we have measurements to make. We can detect the bias. We can work to correct for it. That possibility will not always be available. The resolution of these questions is already underway. Next-generation observatories are extending our reach far beyond the void's boundaries, providing measurements of cosmic expansion and galaxy distribution that are not contaminated by our local environment. The Vera Rubin Observatory, with its massive mirror and extraordinarily wide field of view, will survey the sky repeatedly and detect millions of galaxies, tracing the cosmic web in unprecedented detail across vast distances. The Euclid Space Telescope is mapping the geometry of the universe by measuring billions of galaxies across tens of billions of light-years of cosmic history, tracking how dark energy has shaped the expansion of space over time. These instruments will allow astronomers to observe galaxies well beyond the void's edge, where local void effects become negligible. If the Hubble tension evaporates as measurements push deeper, if the local expansion rate converges toward the lower value predicted by the microwave background once we reach distances of 3 or 4 billion light-years, the void hypothesis will receive strong confirmation. The tension will turn out to have been a measurement artifact, produced by our unusual position, rather than a sign of new fundamental physics. If, however, the tension persists, even at great distances, if the universe continues to show conflicting expansion rates, no matter how far we measure, then something more fundamental is wrong. Dark energy may evolve over time, rather than remaining constant. Gravity may behave differently on cosmic scales than general relativity predicts. There may be components of the universe we have not yet identified. The void hypothesis and new physics are not mutually exclusive. Both could contribute. On the theoretical side, cosmologists are building more sophisticated models of how voids affect observations. These models must account for the velocity fields voids create, how those velocity fields modify apparent expansion rates, and how the effects differ across different types of measurements. Computer simulations are running virtual universes with voids of different sizes and depths, predicting what observers inside those voids should measure, and comparing those predictions to real observations to test whether our understanding of void formation and evolution is correct. The precision of these comparisons will improve substantially as new surveys deliver their data. The Dark Energy Spectroscopic Instrument has already mapped tens of millions of galaxies, providing three-dimensional maps of cosmic structure with unprecedented coverage and accuracy. Future instruments will extend that reach further, sampling the universe at distances where local void effects are negligible and global cosmological properties dominate. What remains genuinely open is not just a set of technical questions about measurement precision. The KBC void raises something more fundamental about the nature of scientific knowledge in a universe where every observer is necessarily embedded within the system being observed. We cannot achieve a view from nowhere. We observe the cosmos from a specific location, at a specific time, through specific instruments, with all the limitations and biases those particulars impose. The history of cosmology is partly a history of recognizing those limitations and developing methods to correct for them. The void is the most dramatic example of this challenge we have yet encountered. Its scale is so vast that it encompasses everything we can comfortably observe without special effort. Its effects are large enough to create a 9% discrepancy in one of the most important numbers in cosmology. Its existence forces us to question whether the measurements that form the foundation of our understanding of the universe are telling us about the universe itself, or about the unusually empty corner of it we happen to inhabit. Yet the story is not one of defeat or uncertainty spiraling into confusion. It is a story of science doing exactly what it is supposed to do: making careful measurements, noticing when they conflict, building models to explain the conflicts, and developing new observations to test those models. The void was discovered through painstaking analysis of 35,000 galaxies. Its implications were worked out through detailed theoretical modeling. Its effects on cosmological measurements were calculated through rigorous mathematics. The tools being deployed to test those models represent decades of engineering and scientific development. The KBC void teaches us that we live in a universe that does not always present itself straightforwardly. The cosmos has a structure that distorts our measurements in ways that took decades to recognize. The expansion rate we thought we were measuring turns out to have been partially a reflection of our unusual location. The tension between different measurement methods, which seem to demand revolutionary new physics, may have a much more prosaic explanation. We were looking through a cosmic lens we did not know we were wearing. What scientists still do not know is precisely how large and how deep the KBC void truly is. Different measurement techniques give somewhat different answers, and the error bars on its properties remain relatively wide. Resolving those uncertainties requires deeper galaxy surveys, extending to distances of 3, 4, 5 billion light-years, providing a baseline outside the void's influence. Scientists also do not yet know whether the void is statistically consistent with standard cosmological models, or whether it genuinely requires modifications to our understanding of gravity or the early universe. That question depends on both better measurements of the void and better calibration of what standard models actually predict for extreme structures. The anthropic question hovers over all of this. Does our presence here tell us something about life in the universe? If voids are statistically rare but favorable for the development of stable, long-lived civilizations, then perhaps observers are more likely to find themselves in voids than random placement would suggest. The quieter environment, the lower radiation exposure, the longer timescales without catastrophic disruptions might all tip the scales toward life arising and persisting in underdense regions. Or perhaps our location is simply improbable, a cosmic lottery we happen to win without any deeper reason. With a sample of only one civilization, we cannot distinguish between these possibilities. The universe is large enough that even very unlikely outcomes eventually occur, and perhaps we simply represent one of the rare observers born into an unusually empty cosmic neighborhood. What is certain is that we are aware of the void, aware of its properties, aware of its effects on our measurements, and actively working to account for all of it. That awareness represents something genuinely remarkable. We are small creatures on a small planet in an ordinary galaxy sitting in an unusually empty region of space 2 billion light-years across. We did not even know our cosmic address until a few decades ago. Now we are mapping the void's boundaries, modeling its gravitational influence, correcting our expansion measurements for its effects, and using it as a laboratory to probe the nature of dark energy and the validity of our theory of gravity. The void surrounds us, but it does not constrain our understanding. Through observation, mathematics, and a willingness to revise our assumptions when the evidence demands it, we are learning to see the universe as it is, rather than as we imagined it from our biased vantage point. The cosmic hole we inhabit is 2 billion light-years wide. We know it is there. We are measuring its properties. We are correcting for its influence. And in doing so, we are building a more honest and more accurate picture of the universe beyond. That work continues. One measurement at a time, one model at a time, one corrected assumption at a time. The void may distort our view of the cosmos, but it cannot stop us from looking. To truly appreciate what the KBC void means for our understanding of the universe, it helps to retrace how cosmologists came to map the large-scale structure of space in the first place. For most of the 20th century, our picture of the universe was built from flat photographs of the sky. Galaxies appeared as fuzzy smudges at various positions. Counting them revealed where they clustered and where they thinned out. But a photograph of the sky is like a painting on a flat canvas. It captures direction, but not depth. Without depth information, you cannot distinguish a cluster of galaxies very close together from a scattered collection of galaxies that happen to fall along the same line of sight, but are separated by hundreds of millions of light-years. The breakthrough came with systematic redshift surveys. When a galaxy is moving away from us, the light it emits is stretched to longer wavelengths by the expansion of space between us and it. This stretching shifts the characteristic spectral lines of atoms toward the red end of the spectrum. The amount of redshift tells you how fast the galaxy is receding, and since cosmic expansion is roughly uniform, faster recession means greater distance. By measuring the redshifts of hundreds, and then thousands, and then hundreds of thousands of galaxies, astronomers gained a third dimension that flat photographs could never provide. In the 1970s and 1980s, early redshift surveys began revealing something startling. Galaxies were not distributed uniformly through space. They were concentrated along flat sheets and long chains, with enormous empty regions between them. The first truly dramatic demonstration came from the Center for Astrophysics Redshift Survey in the early 1980s, which revealed a feature quickly named the Great Wall, a vast, flat concentration of galaxies stretching across hundreds of millions of light-years. The empty regions on either side were correspondingly enormous. These early results were initially met with skepticism. The structures seemed too large to be consistent with theoretical models of how gravity operates over cosmic time. But subsequent surveys confirmed and extended the picture. By the mid-1980s and 1990s, the cosmic web had revealed itself unmistakably. The universe was not smooth. It was organized into a hierarchy of structures, from individual galaxies to groups to clusters to superclusters, all threaded together by filaments and separated by vast voids. The Sloan Digital Sky Survey, beginning in the year 2000, transformed cosmology in the same way that systematic measurement in any field transforms understanding, by turning impressionistic observations into precise, quantitative data. Over more than a decade, the survey measured the spectra of nearly 3 million galaxies, creating a three-dimensional map spanning billions of light years. This map revealed the cosmic web in extraordinary detail. Filaments twisting and branching across the sky like luminous rivers, voids appearing as dark spherical bubbles sometimes 500 million light-years across, and the largest structures, including the Sloan Great Wall, a filament nearly 1.5 billion light-years long. With this map in hand, cosmologists could do something genuinely powerful: compare the observed structure to the predictions of theoretical models. The standard model of cosmology, known as lambda cold dark matter, makes specific predictions about how structure should develop from the initial quantum fluctuations of the Big Bang. The predictions match the observations remarkably well in most respects. The general architecture of the cosmic web, the typical sizes of voids, the typical lengths of filaments, all emerge naturally from the mathematics of gravitational collapse applied to an initially nearly smooth universe. The KBC void emerges from this context as an anomaly within an otherwise successful framework. Most voids in the universe are smaller and shallower than the structure surrounding us. The standard model predicts that large, deep voids should be exponentially rarer than small, shallow ones, because large voids require an exceptionally underdense initial seed, and the initial quantum fluctuations are randomly distributed according to well-understood statistical laws. Finding a void as large and as deep as the KBC void is, by this reasoning, statistically extraordinary. To make this concrete, in the standard model of cosmology, the probability distribution for large-scale density fluctuations follows what statisticians call a Gaussian distribution, a bell curve centered on zero deviation from average. Small deviations from average are common. Large deviations are exponentially rare. When cosmologists calculate where the KBC void falls on this probability distribution, the result is deeply uncomfortable. The observed underdensity, spread over the observed volume, is several standard deviations from average, in some analyses approaching 10 standard deviations. In a standard Gaussian distribution, a 10 standard deviation event has a probability so small it essentially never occurs in a finite universe. But wait, there is a subtlety here that cosmologists argue about intensely. The probability calculation depends on exactly how you measure the void's properties. Different methods of estimating depth and extent give somewhat different numbers. The most alarming estimates assume the void is both very deep and very large. More conservative estimates, which some researchers argue are more appropriate, suggest the anomaly is merely several standard deviations rather than 10. Several standard deviations is still very unlikely, but not logically impossible even within the standard model. This quantitative uncertainty makes the void both scientifically important and scientifically contentious. If the void is genuinely 10 sigma, that is almost certainly a sign that something is fundamentally wrong with our cosmological model. If it is 3 or 4 sigma, it might be rare, but within the statistical distribution expected in a universe as large as ours, the universe contains an enormous number of regions. Even events with probability of 1 in a million will happen countless times across the observable cosmos, which contains hundreds of billions of galaxies organized into countless voids of various sizes. Resolving this quantitative uncertainty is one of the primary scientific motivations for building the next generation of galaxy surveys. Precisely characterizing the void requires measuring galaxy distributions to distances well beyond its boundaries, so that the void shows up clearly as a coherent, underdense region against a well-characterized cosmic average. Current surveys are adequate to demonstrate the void's existence, but not yet to nail down its properties with sufficient precision to definitively rule it in or out as a standard model anomaly. The interplay between the void and dark energy deserves deeper examination because it connects our local cosmic address to one of the most important and most poorly understood components of the universe. Dark energy was not even known to exist until 1998, when 2 independent teams of astronomers measuring the distances to Type Ia supernovae at high redshifts made a discovery that changed cosmology overnight. Instead of the universe's expansion slowing down over time, as would be expected if gravity were the only relevant force, the expansion was speeding up. The supernovae were dimmer than expected, which meant they were farther away than expected, which meant the universe had expanded more rapidly in the recent past than the rate of expansion measured closer to us would suggest. This acceleration required a new component in the universe's energy budget. Something was pushing space apart at an accelerating rate, something that behaves unlike ordinary matter or energy, something that does not dilute as the universe expands, but maintains a roughly constant energy density even as space grows larger. This mysterious component was called dark energy, and subsequent measurements have confirmed it accounts for approximately 68% of the universe's total energy content. Ordinary matter, including all the galaxies, stars, planets, gas, and dust we can observe, accounts for only about 5%. The remainder is dark matter, a form of matter that interacts gravitationally but not electromagnetically, producing no light and remaining detectable only through its gravitational effects. Dark energy's precise nature remains one of the deepest open questions in all of physics. The simplest explanation, that dark energy is a property of empty space itself, a constant energy density built into the vacuum, is consistent with observations but theoretically troubling. Quantum field theory predicts that empty space should have an enormous energy density due to quantum fluctuations of every field that exists. The predicted vacuum energy density is larger than the observed dark energy density by a factor of roughly 10 to the power of 120. This is the largest discrepancy between theory and observation in the history of physics. Somehow, almost all of the theoretical vacuum energy cancels out, leaving only the tiny remnant we observe as dark energy. No one understands why. An alternative is that dark energy is not a constant, but a field that varies in space and time, sometimes called quintessence. If dark energy is a dynamic field, rather than a fixed vacuum property, its strength could be different in different regions and at different cosmic epochs. This would have implications for how voids evolve compared to dense regions, since the local value of dark energy would affect the local rate of expansion. Testing for variations in dark energy requires measuring cosmic expansion precisely across many different environments and time periods, which is exactly what the combination of void studies and deep galaxy surveys can provide. Within voids, where matter density is low and dark energy dominates, the expansion is driven almost entirely by dark energy's repulsive effect without the moderating influence of gravity. The void expands, its walls push outward, and the rate of that expansion encodes information about dark energy's current strength. By comparing expansion rates at the same cosmic epoch measured in different environments, with different amounts of matter, scientists can test whether dark energy is the same everywhere or varies across space. Any variation would be a profound discovery, suggesting dark energy is not a property of space-time itself, but a physical field with dynamics of its own. The dark energy spectroscopic instrument is already gathering this information at unprecedented scale. By mapping tens of millions of galaxies and measuring baryon acoustic oscillations with extraordinary precision at multiple cosmic distances, it is building a three-dimensional picture of how dark energy has shaped the universe's expansion history over billions of years. If dark energy has varied over time or across space, the evidence should show up as subtle deviations in how the characteristic scale of baryon acoustic oscillations appears at different distances. The survey is scheduled to operate through the mid-2020s, and its results will fundamentally reshape our understanding of dark energy and its role in cosmic evolution. The Vera Rubin Observatory, situated on a mountain in Chile and scheduled to begin its main survey of the southern sky within the next few years, will complement this picture from a different angle. Rather than measuring individual galaxy spectra, it will image billions of galaxies repeatedly over a decade, searching for supernovae, studying the shapes of galaxies to measure weak gravitational lensing, and mapping the three-dimensional distribution of matter across the sky with extraordinary coverage. Its particular value for the void question lies in its ability to trace the cosmic web out to very large distances, providing the baseline measurements needed to characterize the KBC void against the broader cosmic structure. The Euclid Space Telescope, launched in 2023 and currently surveying a large fraction of the sky from its orbit around the Sun, is mapping the geometry of the universe by measuring the shapes and positions of billions of galaxies across about 10 billion light-years of cosmic history. Weak gravitational lensing, the subtle distortion of distant galaxy shapes by the mass of foreground structure, is Euclid's primary tool for measuring how dark energy has affected the growth of structure over cosmic time. Combined with baryon acoustic oscillation measurements from galaxy clustering, Euclid will provide the most precise constraints yet on dark energy's properties, and on whether the standard cosmological model is adequate to explain the universe we observe. Within about 10 years, the combined data from these instruments should be sufficient to definitively answer whether the Hubble tension is explained by the KBC void or whether new physics is required. The test is conceptually simple. If the measured expansion rate converges to the lower value suggested by the cosmic microwave background once observations extend beyond 2 billion light-years, the void hypothesis is confirmed. The local measurements will have been proven to be biased by our unusual location, and the true expansion rate will be the one free from that local contamination. The Hubble tension will dissolve, not because of new physics, but because of better understanding of an observational bias. If instead the tension persists at all distances, new physics becomes essentially unavoidable. The universe would be genuinely expanding faster now than the early universe measurements predict, and no known mechanism within the standard model can produce this without significant modifications to our understanding of dark energy, gravity, or the matter content of the universe. There is also the possibility of a middle ground. Measurements might show that the void accounts for some, but not all of the tension, with the remainder requiring genuine new physics. This mixed outcome would be scientifically very fertile. It would tell us both that our local environment is unusual, and that there is something beyond standard cosmology to discover. Distinguishing between these outcomes requires exactly the precision and scale that the next generation of surveys is designed to provide. The history of cosmology is dotted with moments when measurements from a restricted vantage point were later revealed to be biased by local conditions. The expansion of the universe itself was discovered partly because astronomers initially focused on a set of galaxies that happened to be dominated by peculiar velocities, creating confusion about the true relationship between distance and recession speed. The cosmic microwave background temperature was initially measured as a perfect blackbody spectrum, but subsequent precision measurements revealed tiny fluctuations that encoded the seeds of all cosmic structure. Dark energy was not even in the theoretical vocabulary when astronomers first began measuring distant supernovae. Each new level of precision has revealed a universe more complex and surprising than the previous level of measurement suggested. The KBC void fits naturally into this pattern. It represents a feature of the universe that was invisible at the resolution of earlier surveys, but becomes unavoidable as measurements deepen and improve. It does not invalidate what came before. It adds a layer of complexity that better measurements were always going to reveal eventually. The earlier cosmological measurements were correct within their scope. They simply failed to account for a local environmental factor that became apparent only when galaxy surveys reached sufficient depth to map the void's extent. This is also why the void story is not primarily a story of cosmology in crisis, despite how it is sometimes described. A scientific field in crisis is one where its fundamental framework fails to explain core observations with no clear path to resolution. The void story is more nuanced. The fundamental framework of cosmology, quantum fluctuations from inflation, gravitational instability, building structure, dark matter providing the scaffolding for galaxies, dark energy driving, accelerating expansion, remains consistent with the vast majority of observations. The void creates a specific, quantifiable problem with a specific, testable resolution. That is not crisis. That is productive scientific progress. Understanding the void's role in the Hubble tension also requires appreciating what the tension has already taught us about the reliability of our measurement methods. Before the tension became apparent, cosmologists sometimes assumed that different methods for measuring the expansion rate were straightforward cross-checks on each other. If multiple independent methods gave the same answer, that answer must be right. The tension revealed that this assumption was too optimistic. Independent methods can share systematic biases if they are all conducted from the same unusual vantage point. The realization that our measurements might be biased by our cosmic location represents a maturation of cosmological methodology. It is not enough to have independent methods. The methods must probe genuinely different physical conditions. The cosmic microwave background method satisfies this criterion because it measures the early universe before voids existed. The local measurement methods do not satisfy it as fully because they all operate within the same underdense environment. Recognizing this distinction has forced cosmologists to think more carefully about what it means for a measurement to be truly independent. This deeper methodological thinking will benefit cosmology long after the specific question of the Hubble tension is resolved. Future measurements will be designed from the outset to probe multiple environments at multiple cosmic distances, providing not just single numbers, but the full environmental dependence of those numbers. This richer picture will be more informative and more reliable than the single number measurements that dominated earlier cosmology. Consider also what the void tells us about the relationship between scales in cosmology. Modern cosmology operates comfortably across an enormous range of scales, from quantum fluctuations smaller than an atomic nucleus in the earliest moments of the universe to structures hundreds of millions of light years across today. The tools for connecting these scales are sophisticated and well tested. The cosmic microwave background encodes information about conditions when the universe was fractions of a second old. Galaxy surveys probe scales of hundreds of millions to billions of light years. The gap between these scales is bridged by detailed theoretical calculations and computer simulations. The KBC void lives in the middle of this scale range, at sizes between the scales probed comfortably by microwave background physics and the scales accessible to individual galaxy surveys. Its existence reveals a gap in our observational coverage. We have exquisite measurements of the very early universe and increasingly good measurements of the large-scale universe, but our characterization of intermediate-scale structure, from a few hundred million to a few billion light years, has been limited by the depths of available surveys. The new generation of telescopes is specifically designed to fill this gap. There is an additional subtlety in how we detect and characterize voids that is worth examining carefully. The KBC void was identified through a statistical comparison. The observed density of galaxies within a certain volume was compared to the expected density from cosmological models. Finding fewer galaxies than expected does not directly prove that the region is genuinely underdense. It could also reflect systematic errors in how distances are calculated, or selection effects in which galaxies are included in surveys, or calibration errors in the standard cosmological model used as a reference. Establishing the void's reality required ruling out these alternative explanations through multiple independent lines of evidence. The observed peculiar velocities of nearby galaxies are consistent with being inside a large underdense region because the gravitational influence of such a region would produce exactly the observed bulk flows outward towards surrounding denser structures. The temperature map of the cosmic microwave background shows cold regions in the sky that align with the directions of the void's extent, consistent with the Sachs-Wolf effect that occurs when photons pass through underdense regions. Baryon acoustic oscillation measurements in the local volume show the characteristic clustering scale shifted in ways consistent with the void's properties. These multiple, independent lines of evidence converge on the same conclusion, making the void's existence much more robust than any single measurement could provide. The convergence of independent evidence is one of the most powerful concepts in science. A single measurement can be wrong for many reasons, including instrumental error, data analysis mistakes, or unforeseen systematic effects. But when multiple, completely independent methods, using different instruments, different physical phenomena, and different observational targets, all point to the same conclusion, the probability of all of them being wrong in the same direction becomes vanishingly small. The KBC void has this kind of multi-method support, which is why most cosmologists accept its existence even while debating its precise properties and implications. The existence and properties of the void also connect to our understanding of inflation, the hypothetical period of exponential expansion in the universe's first tiny fraction of a second. Inflation is the leading explanation for several features of the observed universe. Its large-scale homogeneity, despite regions that were causally disconnected at the time of the Big Bang, the flatness of spacetime on large scales, and the spectrum of quantum fluctuations that seeded all subsequent structure formation. The statistical properties of those fluctuations, specifically how their amplitude varies with scale, carry a signature of inflationary physics that cosmologists have worked to measure and characterize precisely. Standard inflationary models predict that quantum fluctuations should be nearly scale invariant, meaning that fluctuations on large scales and small scales should have nearly the same amplitude when measured in the appropriate way. This prediction is well supported by microwave background data, but the predicted distribution of large-scale underdensities, which are the seeds that eventually grow into voids, follows from this scale invariance in a specific way. If the KBC void is as extreme as some analyses suggest, it might indicate that the initial fluctuation that seeded it was larger than standard inflationary models predict, hinting that the details of inflation may differ from the simplest models. This connection between the void and inflationary physics is speculative, but scientifically meaningful. The same surveys that will characterize the void's properties will also measure the large-scale distribution of matter with sufficient precision to test whether the spectrum of initial fluctuations follows the simple scale invariant form predicted by the most basic inflationary models, or whether there are deviations at large scales that hint at more complex inflationary dynamics. These measurements will connect cosmological observations of the present-day universe back to conditions in the first fractions of a second of cosmic time. The story of the KBC void is, in microcosm, the story of how scientific understanding advances. It begins with an observation. The universe near Earth looks different from what models predict. It proceeds through the accumulation of independent evidence confirming that the observation is real. It generates specific, testable hypotheses about the observation's cause and consequences. It motivates new measurements designed to test those hypotheses. And it opens connections to deeper questions about the nature of the universe that were not apparent before the original observation was made. The Hubble tension will eventually be resolved, one way or another. Either the void will prove sufficient to explain the discrepancy, in which case cosmology will emerge with a more sophisticated understanding of how local environments bias observations, or the tension will persist beyond the void's influence, demanding new physics that extends our understanding of dark energy, gravity, or the matter content of the universe. Either outcome advances our knowledge. Either outcome is the product of the same basic scientific process that has driven cosmology from a discipline based on naked-eye observations of the night sky to a precision science capable of measuring the age of the universe to within a fraction of a percent. We live inside a hole in space 2 billion light-years across. We know this. We are measuring its properties, correcting for its effects, and using it to test our deepest assumptions about the cosmos. The knowledge itself, arrived at through decades of careful observation and theoretical development, is one of the more extraordinary things about our situation. We are small, brief creatures on an unremarkable planet in an ordinary galaxy, embedded in one of the emptiest regions of an almost incomprehensibly vast universe. And we know it. That knowing, incomplete and provisional and continuously improving as all scientific knowledge is, represents something genuinely remarkable about what minds embedded in matter can accomplish when they look outward, with sufficient care and sufficient curiosity to see the universe as it truly is. Let us go deeper into what the cosmic web actually looks like, and how astronomers have come to understand its detailed architecture, because the void we inhabit makes more sense when you see it as part of this larger structure, rather than as an isolated anomaly floating in an otherwise uniform cosmos. Picture the universe at the largest scales accessible to observation. You are looking at a region perhaps 5 billion light-years across. Within that volume, matter is organized not randomly, but into a specific kind of geometry that has been called the cosmic web. Though describing it as a web perhaps understates how much of the volume is utterly empty space. A better mental image might be soap foam, a collection of large bubbles pressed together, with their thin bubble walls forming the places where matter concentrates, and the interiors of the bubbles representing the vast empty voids. Each bubble is a void, perhaps 200 to 500 million light-years across. The thin walls between adjacent bubbles are the galaxy filaments and sheets. The corners where multiple bubbles meet are the galaxy clusters, the densest nodes in the cosmic web. The Milky Way, Andromeda, and the rest of the local group occupy a relatively minor position in this architecture. We are nowhere near one of the great galaxy clusters. The nearest major cluster to us, the Virgo cluster, contains more than 1,000 galaxies within a region roughly 8 million light-years across. It sits about 53 million light-years away, which in the cosmic web context means it is a nearby but not especially dominant gravitational structure. Beyond Virgo, the Coma cluster, containing more than 1,000 galaxies compressed into a region even denser than Virgo, lies about 320 million light-years away. These clusters and others are connected by the filaments of Laniakea, the supercluster that serves as our local cosmic neighborhood. All of this rich structure, Virgo, Coma, the filaments of Laniakea, the surrounding galaxy groups and clusters, resides within the boundary of the KBC void. The void is not empty of all structure. It contains structure, but the average density of matter within it, when you average over its full 2 billion light-year extent, is about 20% below the cosmic mean. The local structures we see are concentrated pockets within a fundamentally underdense ocean. This hierarchy of structure within structure is characteristic of the universe at nearly all scales. Galaxies cluster into groups. Groups cluster into clusters. Clusters connect into superclusters. Superclusters are organized into the nodes and filaments of the cosmic web. And now we know that even the arrangements of superclusters can define larger patterns of density variation, like the vast underdensity that constitutes the KBC void. The physics that produces this hierarchy is the same at every level, gravity amplifying tiny initial density differences over billions of years. A region that started slightly overdense attracted more matter, grew denser, attracted still more matter. This positive feedback drove the collapse of the most overdense regions into the first objects, while the matter they attracted drained away from the surrounding regions. The regions losing matter became the progenitors of voids. The regions gaining matter became the progenitors of filaments, clusters, and the densest nodes of the cosmic web. Computer simulations of this process are among the most visually striking products of modern cosmology. Starting from the initial conditions derived from the microwave background, researchers let gravity operate in a simulation containing billions of computational particles representing dark matter, ordinary matter, and dark energy. Over billions of simulated years, the initial smooth distribution of particles evolves into a recognizable cosmic web, clusters blazing with virtual galaxies at the intersections of filaments, and between them, the dark, nearly empty voids that dominate the volume. The resemblance between these simulations and actual galaxy surveys is striking, demonstrating that the basic physics driving structure formation is well understood. The same simulations allow cosmologists to study the statistical distribution of void sizes and densities in a universe governed by the standard cosmological model. And this is where the KBC void creates tension. The simulations almost never produce a void as large and as underdense as the KBC void within a universe-sized box. The void falls in the extreme tail of the probability distribution. Whether this means the standard model is wrong, or just that we got unlucky in the cosmic lottery, is the central unresolved question. To understand the peculiar velocity flows that the KBC void generates, think about what happens to a galaxy sitting inside an underdense region. From every direction, the galaxy is surrounded by less than average matter nearby, and more than average matter far away at the void's edges. The gravitational pull from the nearby matter is weaker than average. The gravitational pull from the distant overdense walls is pulling outward. The net effect is a persistent acceleration that pushes the galaxy away from the void's center and toward the surrounding dense filaments. This is not a small effect. The gravitational influence of a void 2 billion light-years across, containing 20% less mass than an average region of that size, is enormous in absolute terms, even if it is subtle relative to the density deficit. The force is diffuse and sustained over enormous distances, acting on every galaxy within the void and generating coherent bulk flows. Entire regions of the cosmos where galaxies are moving systematically in the same direction, pushed outward by the void's gravitational imbalance. The Cosmic Flows project, led by Brent Tully and his colleagues, has been the primary scientific effort to map these bulk flows observationally. By measuring the distances to thousands of galaxies using multiple independent techniques, and comparing those distances to the galaxy's recession velocities, the project can calculate the peculiar velocity of each galaxy, the component of its motion, not explained by cosmic expansion, but driven by local gravitational dynamics. When these peculiar velocities are mapped in 3 dimensions, they reveal a coherent pattern of motion consistent with what you would expect from a galaxy inside a large, underdense region. The velocities are largest near the void's edges, where the density gradient between the void's interior and the surrounding filaments is steepest. They are smaller near the void's center, where the gravitational pulls from all directions largely cancel out. Our galaxy sits between the center and the edge of the KBC void, which means we experience a moderate but significant net outward push. The local group is moving at several hundred kilometers per second, relative to what the pure cosmic expansion would predict, driven by the combined gravitational effects of the local void, the KBC supervoid, and the overdense structures beyond both. This motion complicates cosmological measurements in a way that was not fully appreciated until recently. When astronomers measure the Hubble constant using local supernovae and Cepheid stars, they are measuring the recession velocities of galaxies at distances up to perhaps 200 million light-years away. If those galaxies are also experiencing peculiar velocities driven by the void's gravitational influence, their apparent recession speed is a combination of cosmic expansion and local dynamics. Separating these two contributions requires either knowing the peculiar velocities independently or measuring far enough out that the peculiar velocity contribution averages out. In a typical, homogeneous region of the universe, peculiar velocities do average out at large distances, But inside the KBC void, the peculiar velocities are coherent rather than random. They do not average out. Instead, they all point in roughly the same direction, outward from the void's center. This coherence means that even when measuring at distances of 200 million light-years, the peculiar velocity contribution has not disappeared. It is still inflating the apparent expansion rate by a systematic amount. The resolution, again, requires measuring at distances where the void's influence becomes negligible, at several billion light-years or more. At those distances, the peculiar velocity field induced by the KBC void has faded, and the measured recession velocities more accurately reflect the universe's global expansion rate. Achieving those distances with sufficient precision to resolve the Hubble tension is the primary technical challenge facing observational cosmology in the coming decade. One of the most elegant aspects of the void story is how it connects to fundamental measurements of dark matter. Dark matter, which makes up about 27% of the universe's energy content, is invisible to direct observation. We infer its existence from its gravitational effects, the rotation curves of galaxies that spin too fast for the observed, visible matter to hold them together, the gravitational lensing of light by clusters that contain far more mass than stars and gas alone can explain, and the pattern of temperature fluctuations in the cosmic microwave background that requires the presence of matter that did not interact with photons in the early universe. In the standard model of structure formation, dark matter is the scaffolding around which visible matter collects. The initial overdense regions that eventually collapse into galaxies and clusters are primarily overdense in dark matter. Visible matter, hydrogen and helium gas in the early universe, falls into the gravitational wells created by dark matter halos and condenses into stars and galaxies at the centers of those halos. Without dark matter's gravitational dominance in the early universe, the visible matter alone would not have had time to form the structures we observe today. Within the KBC void, dark matter is present, but at only about 15% of its cosmic average density. The dark matter that originally occupied the void's volume has largely been drained away into the surrounding filaments and clusters over billions of years of gravitational evolution. This drainage is exactly what the standard model predicts for underdense regions. It is the same process that creates visible galaxy voids. The dark matter and gas are both drawn toward the overdense regions that eventually become filaments and clusters. The visible galaxy distribution we observe is a direct tracer of the underlying dark matter distribution, which is why measuring galaxy counts reveals the void's existence. This connection between visible matter and dark matter is exploited by gravitational lensing measurements, which are rapidly becoming one of the most powerful tools in cosmology. When light from distant galaxies passes through the foreground distribution of matter, both dark and visible, the matter's gravity subtly deflects the paths of the photons. This deflection distorts the apparent shapes of background galaxies in a way that depends on the mass distribution along the line of sight. By measuring the shapes of millions of background galaxies and looking for correlated distortions, astronomers can map the foreground mass distribution, including its invisible dark matter component. Applied to the KBC void, gravitational lensing measurements show that the underdensity in visible galaxies is matched by an underdensity in total mass, consistent with the void being a genuine deficit in both dark and visible matter, rather than some unusual condition where visible matter is absent but dark matter is present at normal density. This convergence between the galaxy distribution and the lensing mass distribution provides strong confirmation that the void is a real feature of the matter distribution, rather than an artifact of how visible galaxies are distributed. Within a dark matter background, that might itself be more uniform. The significance of the KBC void also extends to studies of galaxy evolution within it. The void is not just a backdrop for cosmological measurements. It is an environment that actively shapes the properties of the galaxies within it. And studying those properties tells us something about how environment influences the development of galaxies and, potentially, about the conditions favorable for the emergence of complex chemistry and life. We have already discussed how void galaxies tend to be smaller, more gas-rich, more slowly evolving, and more metal-poor than their counterparts in dense cluster environments. But there is additional richness in these environmental effects worth exploring. The isolation of void galaxies has preserved them in a sense. They have not been subjected to the violent mergers, tidal stripping, and ram pressure effects that reshape galaxies in dense clusters. Many void galaxies retain the pristine spiral morphologies and regular rotation patterns of galaxies that have evolved undisturbed. Studying these galaxies is like examining fossils of early cosmic structure, galaxies that have changed relatively little since they formed billions of years ago. This fossilization has a counterpart in their star formation histories. Cluster galaxies experience bursts of star formation triggered by mergers and interactions, followed by rapid consumption of gas, and eventual quenching when the gas is exhausted or stripped away. Void galaxies undergo a slower, more continuous star formation history, building their stellar mass gradually over billions of years without the dramatic episodes that punctuate cluster galaxy evolution. This difference in star formation history leaves traces in the colors and spectral properties of void galaxies that can be measured in large surveys. One unexpected finding from surveys of void galaxies is that a small but statistically significant fraction are actively forming stars at rates that seem too high for their isolated environments. These starburst void galaxies have somehow retained or accumulated large reservoirs of neutral hydrogen gas and ignited vigorous star formation through mechanisms that operate purely internally, without the external triggers from interactions or mergers that drive star formation in dense environments. Understanding what triggers these internal star formation episodes in isolation is an active area of research with implications for how galaxies regulate their own growth. The void's influence on star formation within our own galaxy is an indirect but interesting consideration. The Milky Way belongs to the local group, which sits within Laniakea, which resides within the KBC void. The reduced density of matter in our large-scale environment has shaped the structure of Laniakea itself, which in turn has influenced how matter has flowed into and out of the local group over billions of years. While the direct connection between the megavoid and conditions within our galaxy is tenuous, it is not zero. The large-scale gravitational environment shapes the smaller-scale environment, which shapes the even smaller-scale environment, all the way down to individual galaxies, and eventually to the conditions within them. This cascade of environmental influence, from the largest cosmic scales down to the scales of individual galaxies, is one of the themes that makes large-scale structure cosmology connect to the broader astrophysical picture. The universe is not composed of independent entities. Galaxies, clusters, filaments, and voids are all parts of a single interconnected system, and conditions at one scale influence conditions at other scales through gravity and the dynamics of matter and energy. Another dimension of the void story, worth exploring in depth, is the nature of dark energy as studied through void expansion. We established earlier that voids are the best natural laboratories for studying dark energy because dark energy dominates in underdense regions where gravity is weak. But the specific way voids expand encodes information about dark energy that goes beyond simply knowing that accelerating expansion exists. The standard assumption is that dark energy is a cosmological constant, an energy density that pervades all of space uniformly and does not change over time. Under this assumption, the rate at which voids expand should follow a specific pattern that can be calculated from general relativity. If dark energy is instead a dynamic field that changes over time or across space, the expansion of voids would deviate from this standard pattern in ways that depend on how dark energy varies. One specific prediction of the cosmological constant model is that the expansion of the universe should have begun accelerating at a particular epoch, roughly 5 to 6 billion years ago, when dark energy's repulsive force became dominant over matter's gravitational attraction. Before that epoch, the universe was decelerating. After it, the universe began accelerating. The precise timing of this transition and the smoothness of the transition are sensitive tests of whether dark energy is truly a constant or a varying field. Measurements of how void sizes have evolved over cosmic time provide one way to test this transition. When astronomers observe voids at large distances, they are looking back in time to epochs when dark energy was less dominant. Comparing the sizes and depth profiles of voids at different cosmic distances, corresponding to different cosmic epochs, reveals how void formation and evolution has changed as the universe transitioned from matter-dominated to dark energy-dominated expansion. Recent analyses have found some hints that the transition may not be as smooth as the simplest cosmological constant model predicts, and that dark energy might be varying over time in ways inconsistent with a pure cosmological constant. The evidence is not yet definitive, and different analyses using different methods give somewhat different results. But if these hints are confirmed by higher precision measurements from the next generation of surveys, they would represent one of the most significant discoveries in physics in decades, implying that dark energy is a physical field with dynamics rather than a fixed property of empty space. The connection between the KBC void and our understanding of what the universe will look like in the far future is one of the more philosophically striking aspects of this story. The void is not just a feature of the present-day universe. It is a window into the ultimate fate of everything. Dark energy is causing the universe to expand at an accelerating rate. Over astronomical time, this accelerating expansion will increasingly isolate structures from one another. Galaxies and galaxy groups that are not gravitationally bound together will be carried apart by the expanding space between them, eventually receding beyond each other's cosmic horizons. The boundary beyond which light emitted today can never reach. Once two structures are separated by more than this horizon distance, they are causally disconnected forever. For structures within cosmic voids, this future isolation will arrive sooner than for structures in dense filaments and clusters. The void environment, already thin of matter and dominated by dark energy's repulsive force, will expand faster than average. The filaments and walls at the void's edges will thin out and eventually dissolve as the galaxies within them are separated by accelerating expansion. The void will grow, consuming the surrounding structure, until its boundaries merge with the boundaries of other expanding voids to form a sea of near nothingness. For our own local group, gravitational binding provides some protection against this cosmic fate. The Milky Way and Andromeda are on a collision course, scheduled to merge in roughly 4 billion years. The merged galaxy, sometimes called Milkomeda in anticipatory shorthand, will be gravitationally held together against the cosmic expansion. It will persist as an island of structure in an increasingly empty universe. But the structures beyond the local group, the Virgo cluster, the rest of Laniakea, the other galaxy groups visible in today's sky, will eventually recede beyond our cosmic horizon, their light permanently redshifted into invisibility. As this receding progresses over tens of billions of years, the observable universe, the sphere within which information can reach us, will contain progressively fewer and fewer galaxies. Stars will exhaust their fuel. Star formation will slow and eventually stop as gas is consumed or expelled. The merged local group galaxy will fade from brilliant blue-white to red to increasingly dim as its remaining stellar population ages and the most luminous stars die without replacement. On timescales of trillions of years, even the low-mass red dwarf stars, which burn so slowly they can last for tens to hundreds of billions of years, will begin to die. The universe will grow dark. On even longer timescales, gravitational interactions within the merged galaxy will gradually eject most stars into intergalactic space, leaving only the central supermassive black hole and the stellar remnants, white dwarfs, neutron stars, and black holes that were too tightly bound to escape. Eventually, through a process called Hawking radiation, predicted by quantum mechanics, even black holes will slowly evaporate, radiating away their mass as a diffuse cloud of particles and photons, over timescales that dwarf the current age of the universe by many orders of magnitude. The final state of the cosmos will be a cold, dark, nearly uniform sea of photons and particles expanding forever into darkness. In that far future, voids will have won decisively. The entire visible structure we observe today, the cosmic web with its billions of galaxies organized into clusters and filaments, will have been dissolved by the relentless expansion of space. The endpoint of all the gravitational organization that built the cosmic web over 13.8 billion years will be a universe more uniformly empty than the KBC void is today. The void we inhabit is not an anomaly at the end of time. It is a preview. This perspective on the void's cosmological significance is not merely philosophical speculation. It informs real scientific questions about when in cosmic history conditions were favorable for the emergence of complexity, life, and intelligence. We exist in a particular window of cosmic time when the universe has had enough time to produce heavy elements through stellar nucleosynthesis, form rocky planets around long-lived stars, and allow the billions of years of biological evolution that produced intelligent life. That window is not infinitely long. In the far future, when star formation has ceased and the universe has grown cold and dark, the conditions for life as we understand it will not exist. We live near the middle of the window during which complex, organized matter like us is possible. Our position within the KBC void connects to this temporal question. The void formed over the last several billion years through the gravitational drainage of matter toward the surrounding filaments. It will continue to expand in the future as dark energy drives accelerating expansion. We inhabit the void at a particular moment in its history, after it has developed sufficiently to influence our cosmological measurements, but before it is dominated so completely that the surrounding structure is no longer visible, the cosmic web is still present. The microwave background is still detectable. The evidence of the Big Bang is still accessible. This combination of a developed void structure with a still observable broader universe is itself a feature of our particular moment in cosmic history. Scientists have occasionally noted the curious fact that we live at precisely the epoch when cosmology is possible. A civilization arising billions of years earlier would face a universe too smooth and too hot for comfortable existence. A civilization arising billions of years later would face a universe so dark and sparse that the evidence of cosmic history would be inaccessible, with no microwave background to detect and no distant galaxies to observe. We sit in the brief interval when the universe's history is still written in the sky. Whether this reflects something more than coincidence is genuinely unclear. The anthropic argument that we find ourselves in conditions suitable for our existence because those conditions were necessary for us to exist provides a logically coherent framework. But it does not tell us whether suitable conditions are rare or common throughout the cosmos, nor whether our particular combination of temporal and spatial circumstances reflects a selection effect or pure chance. These questions will become more tractable as exoplanet science matures, and we begin to understand how common are the conditions that support biology, and as searches for other technological civilizations either find them or constrain how rare they might be. The KBC void has also stimulated renewed interest in alternative models of the universe's large-scale structure, particularly models that modify the statistical properties of initial quantum fluctuations. The simplest inflationary models produce fluctuations with what is called a Harrison-Zeldovich spectrum, where the amplitude of fluctuations is roughly the same on all scales when measured in an appropriate dimensionless way. This prediction matches the microwave background observations remarkably well on the scales those observations can probe. But the microwave background is limited in what scales it can access. The KBC void probe scales much larger than those well characterized by the microwave background. And if the void is genuinely anomalous, it might indicate that the fluctuation spectrum deviates from the simple Harrison-Zeldovich form on these larger scales. Such deviations could arise in modified inflationary models, where the inflaton field, the hypothetical field that drives inflationary expansion, has features or transitions in its energy landscape that alter the amplitude of fluctuations at specific scales. They could also arise from primordial non-Gaussianity, a deviation from the assumption that initial density fluctuations follow a simple Gaussian statistical distribution. Detecting primordial non-Gaussianity would be a major discovery, providing direct information about the physics of inflation that no other observation currently can access. Measurements relevant to these questions come from comparing the observed distribution of very large structures with theoretical predictions. The sizes and depths of the largest voids, the clustering properties of galaxy clusters, the distribution of the very largest filaments and superclusters, all carry information about the initial fluctuation spectrum on large scales. As surveys extend to billions of light years and characterize structure on scales comparable to the KBC void size, they will provide the most powerful constraints yet on the statistical properties of the primordial fluctuation field and the physics of inflation. The question of whether the void violates the cosmological principle is worth examining with more precision than simply noting that the principle says the universe should be homogeneous and the void is not homogeneous. The cosmological principle is a statement about averages over large scales, and the relevant question is, what scale is large enough for the averages to be meaningful? In a universe where density fluctuations exist at all scales, some scale of averaging will always be large enough to smooth out local anomalies. The question is whether the averaging scale at which homogeneity holds is smaller than or larger than the scale of the KBC void. Most theoretical analyses suggest that homogeneity should hold on scales of a few hundred megaparsecs, or larger, where a megaparsec is about 3.26 million light-years. The KBC void is about 600 megaparsecs across, which places it right at the boundary of where homogeneity is supposed to apply. This means the void is not clearly within the homogeneous regime, but neither is it clearly violating homogeneity on scales where it is well established. It sits in an uncomfortable middle ground, where the theoretical predictions are not precise enough to definitively say whether the void is a violation of the cosmological principle or a permitted extreme in a universe where the principle applies only at larger scales. This ambiguity is another reason why precise, quantitative characterization of the void is so scientifically important. If the void is genuinely anomalous relative to the predictions of standard cosmology, even accounting for the finite size of the observable universe and the inherent statistical variance in structure formation, then one of two conclusions follows. Either the cosmological principle breaks down at scales smaller than the void, meaning the universe has genuine large-scale inhomogeneity that is not a statistical fluctuation, or the cosmological principle holds. But the standard model of cosmology is incorrect about what level of inhomogeneity is statistically expected at these scales, perhaps because of incorrect assumptions about dark energy, dark matter, or initial conditions. Either conclusion would be scientifically transformative. The first would require a major revision to one of the foundational principles of modern cosmology. The second would require revisions to the specific physical model built on that principle. Both paths lead to new physics and new understanding. The scientists working on these questions are not operating in a vacuum of confusion. They have a clear roadmap. The data that will resolve the KBC void status within cosmology is being collected right now. The analytical techniques for comparing observations to theoretical predictions are being developed and refined. The theoretical models being tested against these observations are growing more sophisticated. Within perhaps 10 years, the combination of data from Euclid, the Vera-Rubin Observatory, the Dark Energy Spectroscopic Instrument, and other projects will have answered the primary questions raised by the KBC void. What we will not know within 10 years is whether our location in this unusually empty region of space has had any influence on the development of life and intelligence. That question sits at the intersection of cosmology, planetary science, astrobiology, and the search for other civilizations, none of which will reach the level of completeness needed for a definitive answer in that time frame. It is a question for a longer future, requiring not just better telescopes, but a fundamentally richer understanding of the conditions that allow life to arise and persist over cosmic timescales. What we can say with confidence is that the KBC void is real, that it influences our cosmological measurements, and that understanding it is essential for extracting the universe's true properties from the observations we make. We have been measuring the cosmos from inside a cosmic hole for as long as we have been making cosmological measurements without knowing we were doing so. We know it now. Every future measurement will be made with that knowledge, improving our ability to correct for its effects and to see the universe more clearly. That is the nature of scientific progress. Not a steady accumulation of certainties, but a repeated process of recognizing the limitations of our current knowledge, developing the tools to overcome those limitations, and arriving at a more accurate and more complete picture of reality. The KBC void is not the end of that process. It is a milestone within it, a recognition of one more way our particular vantage point shapes what we see, and one more example of how carefully examining the universe from where we are can reveal truths that extend far beyond our immediate cosmic neighborhood. There is something profound about standing at the threshold of what we know and peering into what we do not. The KBC void sits at exactly that threshold. On one side lies the universe, as we have mapped it from within. Our galaxy, our supercluster, the surrounding web of filaments, all of it embedded in the gentle underdensity that has been subtly shaping our measurements since the first astronomers began counting galaxies. On the other side lies the universe, as it actually is. Its true expansion rate, its correct age, its genuine distribution of matter across scales, we are only now beginning to probe with sufficient depth. The tools cosmologists have developed to cross that threshold are worth examining in detail because they represent some of the most ingenious scientific instruments ever constructed. And understanding how they work illuminates why the void's effects are so difficult to disentangle from the universe's global properties. The cosmic microwave background, the faint bath of thermal radiation that fills the sky uniformly in every direction, is the oldest light in the universe. It was released approximately 380,000 years after the Big Bang, when the universe had cooled just enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was an opaque plasma, and photons could not travel freely. They were constantly scattered by the free electrons. As long as photons could not travel freely, they were trapped within the plasma, bouncing around and carrying energy with them, but unable to escape to distant regions of the universe. When neutral hydrogen formed, the plasma became transparent almost instantaneously in cosmological terms. Photons that had been bouncing around in the plasma were suddenly free to travel unimpeded in whatever direction they happened to be moving. They have been traveling ever since, for 13.8 billion years. and we detect them today as a uniform background of microwave radiation filling the sky. The uniformity of this radiation reflects the smoothness of the early universe. The tiny temperature variations, 1 part in 100,000, reflect the quantum fluctuations that seeded all subsequent structure. This ancient light carries no information about structures that formed after it was released. It does not know about the KBC void, which formed over the last several billion years. Measurements of the microwave background's temperature fluctuations probed the physics of the universe when it was 380,000 years old, long before voids of any significant size existed. This is precisely why the microwave background method for measuring the Hubble constant is unaffected by our void location. It is measuring the universe as it was before the void formed. The opposite is true for local distance measurements using supernovae and Cepheid stars. These measurements probe the universe as it is today, within the last few billion years, within the volume of space that is dominated by the KBC void. They measure how fast galaxies are receding from us right now, and the answer they give includes both the universe's global expansion and the extra outward push from the void's gravitational influence. Type Ia supernovae are particularly valuable as cosmological distance indicators because of a remarkable property of the physics that produces them. When a white dwarf star in a binary system accumulates enough mass from its companion to exceed a critical threshold of about 1.4 times the mass of the Sun, it undergoes a runaway nuclear fusion reaction and explodes with a characteristic luminosity. Because the ignition occurs at essentially the same critical mass every time, the intrinsic brightness of these explosions is nearly uniform across cosmic history. A type Ia supernova in a galaxy 1 billion light-years away shines as brightly in absolute terms as one in a galaxy 100 million light-years away. By comparing how bright they appear in the sky to how bright they must actually be, astronomers can calculate distances with a precision that was revolutionary when the technique was developed in the 1990s. When the teams led by Saul Perlmutter and Brian Schmidt discovered in 1998 that distant supernovae were dimmer than expected given the measured cosmic expansion rate, they were finding that the universe had expanded more than expected over the time it took those supernovae's light to reach us. The implication was that cosmic expansion had been accelerating, and the discovery earned them the Nobel Prize in Physics in 2011. This work also provided one of the most important calibrations of the Hubble constant using local supernovae, and it is precisely these local calibrations that are now implicated in the Hubble tension. Cepheid variable stars offer a different and complementary approach to measuring distances. Cepheids are stars that pulsate in brightness with extraordinarily regular periods, and the period of their pulsation is directly related to their intrinsic luminosity. A Cepheid that brightens and dims with a period of 30 days is intrinsically much more luminous than one with a period of 3 days. Henrietta Leavitt discovered this period luminosity relationship in the early 20th century by studying Cepheids in the Small Magellanic Cloud, a satellite galaxy of the Milky Way. Since all the Cepheids in the Magellanic Cloud are at essentially the same distance from us, differences in their apparent brightness reflect differences in intrinsic brightness, and Leavitt noticed the correlation with pulsation period. This discovery allowed astronomers to measure distances to galaxies by identifying Cepheids within them, measuring their pulsation periods, calculating their intrinsic luminosities from the period luminosity relation, and comparing intrinsic to apparent brightness. Edwin Hubble used this technique in the 1920s to establish that the Andromeda Nebula was far outside the Milky Way, settling the great debate about whether nebulae were nearby clouds within our galaxy, or distant island universes in their own right. Today, Cepheid distances are measured to galaxies tens of millions of light-years away using space telescopes, and those distances are used to calibrate the supernovae distance ladder, anchoring the local measurement of the Hubble constant. Both of these local methods, Cepheid distances and supernova distances, measure within the volume of the KBC void. The peculiar velocities generated by the void's gravitational influence systematically inflate the apparent recession speeds of galaxies relative to their true distances, producing a Hubble constant measurement that is higher than the universe's global expansion rate. The amount of inflation depends on the void's size, depth, and the exact distribution of the galaxies being measured. When cosmologists calculate the expected effect of a void with the KBC void's measured properties, they find it could account for much, or potentially all, of the observed 9% discrepancy between local and microwave background measurements. There are, however, complications that prevent the resolution from being completely clean. The void's properties are themselves measured using galaxy surveys and velocity maps that have their own systematic uncertainties. The depth and extent of the void are not perfectly known. Different analyses give somewhat different answers for these properties. And the uncertainty in the void's properties translates into uncertainty about how much of the Hubble tension it can explain. Some analyses suggest the void can explain essentially all of the tension. Others suggest it can explain only part of it, leaving some residual discrepancy that might require new physics. Resolving this quantitative uncertainty requires both better characterization of the void itself and more precise local measurements of the Hubble constant that can be confidently placed within the void's gravitational context. Measurements of the cosmic distance ladder using the James Webb Space Telescope, launched in 2021, are providing unprecedented precision by observing Cepheid stars and galaxies much farther away than previous telescopes could reach. These measurements are testing whether systematic errors in the Cepheid distance scale might be contributing to the Hubble tension, complementing efforts to understand the void's gravitational influence. The James Webb Space Telescope has also been used to study the oldest and most distant galaxies ever observed, providing new windows on the early universe that complement microwave background measurements. Some of its early results have raised questions about whether the standard cosmological model correctly predicts the properties of the first galaxies to form after the Big Bang. Observations have found galaxies that appear surprisingly massive and mature at very high redshifts, corresponding to times when the universe was only a few 100 million years old. If confirmed, this would suggest that galaxy formation proceeded more rapidly in the early universe than standard models predict, hinting at possible modifications needed in our understanding of how dark matter halos form and how gas within them converts to stars. These early universe surprises are not directly connected to the KBC void, but they add to a broader picture of modern cosmology as a science actively confronting anomalies at multiple scales and epochs. The void is the most dramatic anomaly affecting measurements of the nearby universe. The early galaxy surprises from the James Webb Space Telescope represent potential anomalies in the distant universe. Whether these different challenges reflect separate issues or symptoms of a single underlying modification to the standard model is an open and very active question. Gravitational waves provide yet another independent window on the Hubble tension. When two compact objects like neutron stars or black holes spiral together and merge, they release an enormous amount of energy as gravitational waves, ripples in the fabric of spacetime that propagate outward at the speed of light. These waves were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, known as LIGO, and since then, dozens of compact object mergers have been detected. When a merger involves two neutron stars, it also produces a burst of light that can be observed across the electromagnetic spectrum. This combination of gravitational wave and electromagnetic observation provides an independent way to measure distance. The gravitational wave signal encodes the absolute distance to the merger directly, without requiring calibration through intermediate distance ladder steps. The electromagnetic signal provides the redshift of the host galaxy, telling us how fast it is receding. Combining distance and recession velocity gives a direct measurement of the Hubble constant, independent of both Cepheid distances and microwave background physics. The first such combined gravitational wave and electromagnetic measurement came from a neutron star merger detected in 2017 in a galaxy about 130 million light-years away. The resulting Hubble constant measurement was consistent with both the local Cepheid-based measurement and the microwave background measurement within its large uncertainties, but the error bars were too large to distinguish between them. As more mergers are detected and localized with better precision, gravitational wave cosmology will provide an increasingly powerful, independent check on the Hubble tension. If gravitational wave measurements, which come from sources scattered across different volumes of space, including both inside and outside the KBC void, consistently give the higher Hubble constant associated with local measurements, that would suggest the tension is not primarily due to the void. If they consistently give the lower microwave background value, or if they show a systematic difference between mergers inside and outside the void, that would strongly support the void hypothesis. Over the next decade, as gravitational wave observatories improve their sensitivity and detect hundreds or thousands of mergers per year, this independent constraint will become very powerful. The story of how we came to understand our position in the cosmic web is also a story about the development of computational cosmology and the increasingly close partnership between theory and observation. Modern cosmological simulations are astonishing feats of engineering and scientific vision. The Illustris project, the Eagle simulation, and the more recent Illustris TNG simulations have modeled the formation and evolution of thousands of galaxies in cosmological volumes, tracking the dynamics of dark matter, ordinary matter, dark energy, stellar feedback, black hole growth, and the complex processes by which gas cools, condenses, and forms stars. These simulations start from initial conditions derived from the microwave background, set at a time when the universe was only a tiny fraction of its current age, and run forward in time through billions of years of gravitational evolution, radiative cooling, star formation, and energetic feedback from supernovae and active galactic nuclei. The resulting virtual universes contain galaxies with a wide range of sizes, morphologies, star formation rates, and chemical compositions that match the observed galaxy population remarkably well. Applied to the question of cosmic voids, these simulations demonstrate that the KBC void's size and depth are at the extreme tail of the distribution of void properties in a standard cosmological universe. They almost never produce structures this large in a single simulation box. This rarity is what makes the void statistically significant. But interpreting the rarity requires careful attention to how representative any single simulation is of the full range of possible cosmic histories. The observable universe represents just one realization of the possible outcomes from the initial quantum fluctuations of the Big Bang. There are, by definition, no other universes we can observe to compare with. This means we are always working with a sample of one when it comes to the largest cosmic structures, and statistical statements about how rare a particular structure is depend on comparing our single observed universe to the distribution of outcomes in theoretical simulations. The rarity of the KBC void is assessed by comparing our universe to many simulated universes, each starting from slightly different initial conditions drawn from the same statistical distribution. The interpretation of this comparison is subtle. Finding that only a small fraction of simulated universes contain a void as large as the KBC void could mean the void is genuinely anomalous, which would suggest the standard model is wrong. It could also mean we got unlucky in the cosmic lottery, landing on an unusual realization of a universe that is otherwise typical. Distinguishing between these possibilities is genuinely difficult with a sample of one. One approach is to look for multiple large anomalies in the same universe. If the universe contains not just the KBC void, but also other structures of similarly extreme size and rarity, the probability of all of them occurring by chance decreases rapidly. The existence of the Eridanus supervoid, the Sloan Great Wall, and several other extreme large-scale structures has been cited as evidence that the universe contains more large anomalies than standard models predict. But this argument requires careful accounting for selection effects. The structures we notice and study are precisely the unusual ones. So the sample of known extreme structures is biased toward extremes. The unbiased test is to characterize the statistical properties of large-scale structure across the entire observable volume, not just the extreme cases that draw attention. Complete surveys mapping the distribution of galaxies across billions of light-years provide the data for this unbiased test. Comparing the resulting statistical characterization of the universe's structure with the predictions of standard models, using all of the structure, not just the extreme cases, will reveal whether the universe as a whole shows more large-scale anomalies than expected. This is fundamentally what the next generation of galaxy surveys, Euclid, the Vera-Rubin Observatory, and the Square Kilometre Array, among others, are designed to do. They will provide the deepest and widest maps of galaxy distribution ever created, enabling statistical characterizations of cosmic structure that have never been possible before. The results will either confirm the standard model's predictions or reveal systematic deviations that demand new physics. Either outcome will be a major advance in our understanding of the cosmos. The Square Kilometre Array is particularly noteworthy in this context because of its unique approach to observing the universe. Rather than detecting the visible light or infrared radiation from stars within galaxies, it will detect the radio emission from neutral hydrogen gas, the 21-centimeter line that hydrogen emits when the electron in the hydrogen atom flips its spin. Neutral hydrogen is the raw material from which stars form, and it is present throughout galaxies and in the intergalactic medium. By mapping the distribution and velocity of neutral hydrogen across the sky out to very large distances, the Square Kilometre Array will trace the cosmic web in a completely different way than optical galaxy surveys, providing an independent check on the structure of the universe and the void hypothesis. The 21-centimeter emission from the intergalactic medium, the diffuse hydrogen gas between galaxies, will also allow the Square Kilometre Array to probe the epoch of reionization, when the first stars and galaxies began to ionize the neutral hydrogen that filled the universe after the Big Bang. This epoch, occurring roughly between 100 million and 1 billion years after the Big Bang, is one of the least well-understood periods of cosmic history. Understanding how the universe transitioned from neutral to ionized will test models of the first stars and galaxies, and provide new constraints on the initial conditions that set the stage for all subsequent structure formation, including the eventual formation of the KBC void. The breadth of scientific investigation that the void has stimulated is itself remarkable. A discovery made by 3 astronomers examining galaxy counts in 2013 has ramified into questions about dark energy, the cosmological constant, the theory of gravity, the age of the universe, the statistical properties of initial conditions, the nature of cosmological measurements, the evolution of void galaxies, the search for life, and the ultimate fate of the cosmos. This is how science works at its best. A single observation, carefully analyzed and followed to its implications, opens doors to questions that were not even on the agenda before the observation was made. The scientists who made this discovery did not set out to challenge the cosmological principle or to resolve the Hubble tension, which was not yet known to be a significant problem in 2013. They were doing the patient, systematic work of mapping the universe, checking models against observations, and reporting what they found. The implications emerged from the data, not from preconceptions. This is what distinguishes genuine scientific discovery from motivated reasoning. The community's response to the KBC void also illustrates something important about how science handles anomalous results. The initial discovery was not immediately accepted as definitive. Other researchers scrutinized the methods, looked for systematic errors, proposed alternative explanations, and conducted independent analyses using different data sets. Some analyses confirmed the void, others questioned its depth or extent. The debate sharpened the science and led to more careful measurements. Over the subsequent decade, the weight of evidence has accumulated in favor of the void's reality, but the quantitative details remain contested, and the debate continues to drive improvement in both observations and theory. This is healthy. Scientific knowledge is not advanced by accepting every surprising result immediately. It is advanced by subjecting surprising results to rigorous scrutiny, trying to find alternative explanations, and accumulating evidence from multiple independent directions until the reality of the phenomenon becomes too well established to doubt. The KBC void is approaching that status. Its existence is accepted by most cosmologists. Its precise properties and significance remain under active investigation. What is certain is that we will not soon return to the comfortable assumption that our location in the cosmos is unremarkable. We know now that we inhabit one of the emptiest regions in the observable universe, that this position has shaped every cosmological measurement we have ever made, and that correcting for this position is necessary for extracting the universe's true properties from our observations. This knowledge changes how cosmology is done. It adds a layer of sophistication to every analysis, a correction term that must be estimated and applied, an uncertainty that must be propagated through every conclusion. But it does not undermine cosmology, it strengthens it. A science that can recognize its own biases and develop methods to correct for them is a science in good health. A science that assumes its vantage point is typical when it might not be, and fails to test that assumption, is a science operating on faith rather than evidence. We tested the assumption. We found it wanting. We are now in the process of building a more accurate picture of the universe that accounts for our unusual position. The void may distort our measurements, but our determination to understand what those measurements really mean is undistorted. We live inside a cosmic hole, 2 billion light-years wide. We know it. We are measuring it, and we are using that knowledge to see the universe more clearly than any observer who came before us. Consider for a moment what it would mean to study cosmology from a different address in the universe. Imagine an astronomer living in a galaxy embedded in one of the great filaments of the cosmic web, surrounded by thousands of neighboring galaxies, with clusters visible in every direction. That astronomer has access to a statistically rich sample of nearby objects. The expansion of the universe is immediately apparent because there are plenty of galaxies at a wide range of distances to measure. The peculiar velocities generated by local density concentrations are present, but they are roughly symmetric, pushing and pulling in many directions, so that averages over the full sky tend to cancel out. The Hubble constant, measured by that astronomer, reflects the universe's global expansion rate more accurately, because the local environment is closer to the cosmic average. Now contrast that with our situation. We sit in one of the emptiest regions in the observable universe. The galaxies we can easily observe at nearby distances are all embedded in the same underdense environment. The peculiar velocities they experience are not symmetric. They are all being pushed outward by the same gravitational gradient, all in the same general direction away from the void's center and toward the surrounding dense filaments. When we average the recession velocities and distances to calculate the Hubble constant, we get a number that includes not just the universe's global expansion, but also the coherent outward push from the void. There is no cancellation because there is no symmetry. This asymmetry is subtle in individual galaxy measurements. Each galaxy is at a different distance and has been influenced by the void to a slightly different degree. But when you combine hundreds or thousands of measurements into a statistical estimate, the systematic bias accumulates. The estimated Hubble constant ends up higher than the true global value, by roughly the amount that has been observed. The void's influence is small per galaxy, but consistent in direction, and consistency compounds over large samples into a significant systematic offset. Recognizing this kind of systematic bias requires the ability to compare measurements made in different environments. For most of the history of cosmology, all our local measurements were made within the same environment without our knowing it was unusual. The comparison that reveals the bias only became possible when measurements of the microwave background reached sufficient precision to provide an independent, environment-free estimate of the Hubble constant. The tension between the local and microwave background measurements is what made the void's influence apparent in retrospect. This is a general lesson about systematic biases in science. They are often invisible until you have a reference measurement made under completely different conditions. The same lesson applies in many other scientific contexts. Clinical drug trials require placebo controls because the expectation of improvement can itself produce improvement, and the true drug effect is only visible against a no-drug baseline. Laboratory measurements require careful calibration against known standards because instruments drift and conditions change, and the drift is only apparent when you compare against something that does not drift. In cosmology, the microwave background measurements serve as the stable reference against which the locally biased measurements can be compared. The CMB, as cosmologists abbreviate it, has been studied with extraordinary precision by a series of space missions. The COBE satellite in the early 1990s first detected the temperature fluctuations in the microwave background that encode the seeds of cosmic structure. WMAP, operating from 2001 to 2010, mapped those fluctuations with much higher resolution and provided the first precise cosmological parameter estimates from microwave background data. The Planck satellite, operating from 2009 to 2013 and analyzing data for several years after, achieved extraordinary precision in measuring the microwave background temperature fluctuations, the polarization of the background radiation, and the statistical properties of the fluctuation pattern. The Planck measurements produced the most precise estimate yet of the Hubble constant from early universe physics, approximately 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. This measurement is based entirely on physics that operated in the first few 100,000 years of the universe, completely independent of anything that has happened in the universe over the subsequent 13.8 billion years. The local measurements, using Cepheid distances and type Ia supernovae calibrated by the SH0ES collaboration led by Adam Rees and others, give a Hubble constant of approximately 73 kilometers per second per megaparsec, also with very small uncertainties. The difference between 67.4 and 73 is small in everyday terms, but enormous in scientific terms, when both measurements claim 1% precision. They are saying different things about the same physical quantity with high confidence, and that conflict demands an explanation. The void hypothesis is the most economical explanation because it does not require inventing any new physics. It says the local measurement is biased by our unusual position, and the bias can be estimated from independent knowledge of the void's properties. The microwave background measurement is unbiased because it does not involve any late universe physics. The conflict is resolved by recognizing that the two measurements are not measuring exactly the same thing. One measures the global expansion rate. The other measures the expansion rate plus a local velocity bias. The alternative explanations for the Hubble tension are considerably more radical. Dark energy could be evolving over time, becoming stronger in the recent universe than in the distant universe. This would mean the universe has been accelerating its expansion more aggressively in recent epochs, making local recession velocities higher than the early universe physics would predict. There is some observational evidence from baryon acoustic oscillation measurements, combined with supernova data, that dark energy may not be a perfect cosmological constant, but the evidence is not yet conclusive. Gravity could behave differently on cosmic scales than general relativity predicts. Modified gravity theories have been proposed that change the way matter and energy curve spacetime at very low density or very large scale, potentially producing an effective expansion history that differs from the general relativistic prediction. Some of these theories naturally produce larger voids as well, which would connect the void hypothesis and the modified gravity hypothesis into a unified explanation. There could be additional light components in the early universe, sometimes called dark radiation, that contributed to the cosmic energy budget in the first minutes or hours after the Big Bang. Such components would affect the expansion rate during the radiation-dominated era and alter the predictions derived from microwave background measurements. Several proposals exist for what this dark radiation might be, including light-sterile neutrinos or other feebly interacting particles. None of these alternatives is as economical as the void hypothesis. They all require introducing genuinely new physics without independent motivation. The void, by contrast, was discovered independently through galaxy surveys and is a real, mapped feature of the universe. Invoking it to explain the Hubble tension requires no new physics, only more careful accounting of known effects. This parsimony is one of the reasons many cosmologists consider the void hypothesis the most compelling explanation currently available. The forthcoming resolution of the Hubble tension is therefore not just a matter of measuring the expansion rate more precisely. It is a test of whether the universe's large-scale structure can account for observational biases of the magnitude implied by the tension. The test requires extending measurements beyond the void's boundary and asking whether the apparent expansion rate changes as we look farther out. If it does, the void is doing exactly what physics predicts. If it does not, something else is going on. This test has already begun, at a qualitative level. Some analyses have found hints that the Hubble constant measured with supernovae at larger distances is slightly lower than the value measured at closer distances, consistent with the void's influence diminishing at large distances. But the evidence is not yet statistically decisive. The upcoming surveys will provide the data to make this test quantitative and definitive. Beyond the Hubble tension, the void's influence on measurements of the matter-power spectrum is another area of active investigation. The matter-power spectrum describes how the amplitude of density fluctuations varies with scale, from the scales of individual galaxies up to the scales of the largest cosmic structures. It is one of the most information-rich summaries of cosmic structure, encoding the combined effects of the initial quantum fluctuations, the growth of structure under gravity, and the effects of dark energy and dark matter. Measurements of the matter-power spectrum can be made using various observational probes, including galaxy clustering surveys, weak gravitational lensing, and the clustering of galaxy clusters. When different methods are compared, there is some evidence for a quantity called sigma-8 tension, a discrepancy between the amplitude of density fluctuations inferred from microwave background measurements and the amplitude measured directly from low redshift observations of the matter distribution. The discrepancy is less dramatic than the Hubble tension, but follows a similar pattern. The local universe appears to show slightly less structure than the microwave background predictions suggest. The KBC void could contribute to this tension as well. An underdense local region would appear to show less structure than average by definition, since the void itself is a deficit in the matter distribution. If our surveys preferentially sample the void's interior, they would underestimate the amplitude of matter fluctuations relative to the cosmic average. The sigma-8 tension might partly reflect the same underlying bias as the Hubble tension, our unusual position in an underdense region that makes local observations of matter look different from what microwave background predictions expect for a typical cosmic volume. Whether the void fully explains the sigma-8 tension or only partially explains it is again a quantitative question that requires detailed modeling of the void's effect on different types of structure measurements. The same surveys that will test the void hypothesis for the Hubble tension will also provide the data needed to test it for the sigma-8 tension. If the void resolves both tensions simultaneously, that would be a strong confirmation of the void hypothesis and a powerful demonstration of its cosmological significance. The practical implications of understanding our cosmic address extend beyond academic cosmology into the broader scientific program of understanding the universe's composition and evolution. Every cosmological constraint we place on the properties of dark energy, dark matter, and neutrinos depends on accurately knowing the universe's expansion, history, and matter distribution. If those measurements are systematically biased by our void location, then our constraints on dark energy and dark matter properties are correspondingly uncertain. Dark matter, for instance, has been characterized primarily through its gravitational effects on the motion of galaxies and the clustering of matter. The relationship between the observed galaxy distribution and the underlying dark matter distribution depends on models of how galaxies form within dark matter halos and how dark matter clusters under gravity. If the local matter distribution is unusual because of the void, then the local relationship between galaxies and dark matter may also be unusual, complicating the inference of dark matter properties from local observations. Similarly, the properties of neutrinos, specifically their total mass, are constrained from the effect of neutrino free streaming on the small-scale structure of the matter distribution. Neutrinos, being extremely light and fast-moving in the early universe, tend to smooth out density fluctuations on small scales. The degree of smoothing depends on the total neutrino mass. Measurements of the small-scale matter power spectrum from galaxy clustering and weak lensing constrain this smoothing and therefore the neutrino mass. If the local matter power spectrum is biased by the void, these neutrino mass constraints need to be reassessed. These connections between the void and fundamental particle physics might seem remote, but they illustrate how cosmological measurements are all interconnected through the standard cosmological model. A bias that enters at one point, the Hubble constant measurement, propagates through the model and affects every parameter that is jointly constrained with it. Understanding and correcting for the void's influence is not just about fixing one number. It is about improving the integrity of the entire cosmological analysis framework. This is part of why the cosmological community has invested heavily in understanding the void and its effects. The payoff of getting this right extends far beyond resolving the Hubble tension. It includes more reliable measurements of dark energy, dark matter, neutrino masses, and the statistical properties of the initial quantum fluctuations. All of these improvements have implications for fundamental physics beyond the standard model, potentially providing evidence for new particles, new forces, or new symmetry principles. The universe we inhabit has proven to be simultaneously more comprehensible and more surprising than the scientists who first developed modern cosmology could have imagined. The broad strokes are clear. The universe began in an extremely hot, dense state about 13.8 billion years ago, expanded and cooled, formed the first atoms and the first stars, built a vast cosmic web of galaxies and voids, and is now expanding at an accelerating rate driven by dark energy. This framework is supported by evidence from dozens of independent observational programs and represents one of the most successful scientific theories in history. Within this successful framework, the KBC void sits as a local complication of extraordinary scale, a reminder that even in a homogeneous universe on the largest scales, our particular location can make the universe look different from any single vantage point. The correction for our unusual position is not trivial. It potentially changes some of the most important numbers in cosmology, but the fact that we can identify the correction, estimate it from independent data, and test our estimates with new observations is a testament to the maturity and rigor of the science. We began measuring the universe from inside a hole without knowing we were inside a hole. We are now in the process of mapping that hole, understanding its physical effects, and correcting our measurements for its influence. When future generations of scientists look back on this period in the history of cosmology, they will likely see it as the moment when cosmology matured from a science that assumed its local vantage point was typical, to a science that rigorously characterized and corrected for the specific properties of that vantage point. That maturation is ongoing. The measurements are being made. The models are being refined. The corrections are being applied. And the universe, stranger and more interesting than we thought, is gradually coming into sharper focus. The question of how observers inside cosmic voids perceive the universe relative to observers elsewhere is not just philosophical speculation. It is a concrete scientific question with testable implications, and exploring it reveals something deep about the relationship between position, perception, and knowledge in an inhomogeneous cosmos. Consider what a civilization in a dense galaxy cluster would observe compared to what we observe from inside the KBC void. Their sky would be filled with nearby galaxies in every direction. They would have no shortage of nearby standard candles for measuring distances. Their peculiar velocity corrections, the adjustments needed to separate cosmic expansion from local gravitational motions, would be complex due to the intense gravity of the surrounding cluster environment, but statistically rich due to the abundance of nearby objects. Their Hubble constant measurement would look different from ours, not because the universe is different, but because their local environment is different. More subtly, the amount of structure they see in their vicinity would be higher than average. Their measurements of the matter-power spectrum, the distribution of cosmic structure across scales, would give a higher value of sigma 8 than the cosmic average. Their measurements of the local expansion rate would be lower than the cosmic average, suppressed by the intense gravitational environment rather than inflated by underdensity. Their cosmology, built on local observations, would be systematically biased in the opposite direction from ours. This thought experiment illustrates a profound point about the nature of cosmological measurements. We have been building our understanding of the universe primarily from local observations. The cosmological principle justified this approach. If the universe is homogeneous, local observations are representative of the whole. But the KBC void demonstrates that the universe is not perfectly homogeneous on the scales we typically probe. Local observations are not representative. They are biased, in our case, toward lower density and higher apparent expansion rates, and potentially in other directions for observers in other cosmic environments. The only truly unbiased cosmological measurement we can make is the cosmic microwave background, because it averages over the entire sky and probes the universe before local structure had formed. Everything else is local, and local means biased by our specific position in the cosmic web. Recognizing this is a significant conceptual advance, one that changes how cosmologists think about which measurements to trust for global cosmological constraints and which measurements reflect local conditions. This recognition does not make local measurements useless. Quite the contrary. Local measurements, precisely because they are biased by local conditions, provide information about those conditions that global measurements cannot. The comparison between local and global measurements is what reveals the properties of our local environment, including the KBC void. The tension between the local and microwave background Hubble constant is not a problem to be eliminated. It is a signal to be decoded. It is telling us something specific and quantitative about the matter distribution in the region of space we inhabit. Similarly, the sigma 8 tension, the slight discrepancy between the amplitude of matter fluctuations inferred from the microwave background and measured locally, is telling us that our local volume contains slightly less structure than the cosmic average. These two pieces of information, higher apparent expansion and lower apparent structure, are exactly what you would expect from an observer inside a large, underdense region. The tensions are not contradictions in the standard model. They are measurements of the void. When cosmologists work to quantify these effects precisely and build them into a coherent picture of our cosmic neighborhood, they are doing something genuinely novel, using the discrepancies between local and global measurements as probes of the specific properties of our local universe. This is a fundamentally different approach from treating the discrepancies as errors to be eliminated. It treats them as data about our position in the cosmic structure. The next 10 to 15 years will see this approach mature significantly. With the full data sets from Euclid, the Vera Rubin Observatory, and the Dark Energy Spectroscopic Instrument in hand, cosmologists will be able to characterize the three-dimensional structure of the universe around us with extraordinary precision, extending from our immediate neighborhood out to billions of light years, where the void's influence becomes negligible. The comparison between local and distant measurements will be made not just for the Hubble constant and sigma 8, but for the full range of cosmological parameters, testing whether the standard model can simultaneously explain conditions inside and outside the void. The result of this program will be a cosmology that knows where it is, not just an average description of the universe as a whole, but a description that specifies, here is what the universe looks like globally. Here is what it looks like in our specific location. Here is the quantified difference between the two. And here is the correction that must be applied to translate local observations into global conclusions. This is a more sophisticated and more honest cosmology than the one we have been practicing, and the void has pushed us toward it. What the universe will reveal as these measurements mature is genuinely unknown. The current best guess, that the void explains most, but perhaps not all of the Hubble tension, might prove correct, or the residual unexplained tension might turn out to require new physics after all. The sigma 8 tension might resolve cleanly once the void's influence is properly accounted for, or it might persist in a form that demands additional explanation. The statistical significance of the KBC void itself might increase as measurements improve, deepening the challenge to standard cosmology, or it might shrink as systematic uncertainties are resolved, bringing the void back within the statistical expectations of the standard model. Science is comfortable with this uncertainty. The entire point of the measurements being planned and executed right now is to replace uncertainty with knowledge, to transform what we guess into what we know. The void is not the end of the story. It is the chapter we are currently writing, with a conclusion not yet visible. But the tools to reach that conclusion are being built, the measurements are being made, and the analysis is proceeding with the rigor and creativity that has driven cosmology from a science of fuzzy photographs to a precision science capable of measuring the universe's age to better than 1%. We live inside a cosmic hole, 2 billion light-years wide. We are small creatures on a small planet in an ordinary galaxy in an unusually empty region of space. And yet, from this unlikely vantage point, through the application of physics, mathematics, and instruments of extraordinary precision, we have mapped the structure of the cosmos on the largest scales accessible to observation, measured the age of the universe to within a fraction of its history, discovered the existence of dark matter and dark energy, and identified the large-scale feature of our own cosmic address that has been quietly biasing our measurements since modern cosmology began. That is not a story of limitation. That is a story of what minds embedded in matter are capable of achieving when they turn their curiosity outward and refuse to stop asking what is really out there. The void surrounds us, but it does not define us. What defines us is the choice to look beyond it. The distance between what we observe and what is real has always been the central challenge of cosmology. Galileo could not see beyond what his lens resolved. Hubble could not measure distances beyond what his instruments reached. Every generation of astronomers has operated at the frontier of what was technically possible, building knowledge layer by layer as the technology advanced and the methods improved. Our generation faces a particular version of this challenge. We have instruments precise enough to detect a 9% discrepancy in the universe's expansion rate. We have surveys deep enough to map the large-scale structure of the cosmos out to billions of light-years. We have computers powerful enough to simulate the formation of entire virtual universes. And we have the theoretical framework to make precise, testable predictions about what those simulations and surveys should find. What we lacked for a long time was the knowledge that our location was unusual. That knowledge, delivered by the patient counting of 35,000 galaxies by 3 astronomers in 2013, turns out to be essential context for interpreting nearly everything else we have measured. The universe did not change when the KBC void was discovered. Our understanding of our place within it changed. That change in understanding requires corresponding changes in how we analyze our data, how we interpret our results, and how we frame our conclusions. The ongoing process of making those changes is cosmology in action. Not cosmology in crisis, but cosmology in the act of growing more sophisticated, more self-aware, and ultimately more accurate. The void is the teacher. The lesson is humility about our vantage point, combined with confidence in the methods we have developed to transcend its limitations. We live inside a cosmic hole, 2 billion light-years wide. We know it, and knowing it, we can see farther than we ever could before. Perhaps the most striking aspect of the KBC void story is not the void itself, but the detective work that revealed it. No single observation established its existence. No single telescope stared into the right patch of sky and saw the emptiness. Instead, the void emerged from the convergence of many different lines of evidence, each contributing a piece to a puzzle that only made sense when assembled together. The galaxy counts that Keenan, Barger, and Cowie compiled showed the first statistical hint of underdensity. The peculiar velocity surveys confirmed that galaxies in the region are moving in directions consistent with living inside an underdense environment. The microwave background cold spots aligned with the regions of lowest galaxy density. The baryon acoustic oscillation measurements showed the characteristic clustering scale appearing different locally than in the distant universe. Each of these observations, made with different instruments, using different physical phenomena, targeting different aspects of the universe, told the same story. This convergence is how science establishes reality for objects we cannot see directly. We cannot visit the KBC void or photograph it from outside. We can only infer its properties from the various ways its existence leaves traces in the data we collect. The more independent traces we find, and the more precisely they all point to the same underlying structure, the more confident we become that the structure is real. The KBC void has passed this test across multiple independent probes, which is why, despite the ongoing debate about its precise properties, virtually no cosmologist seriously doubts its existence anymore. The remaining questions are quantitative. How deep exactly? How wide exactly? How does its depth vary across its extent? How does its boundary transition into the surrounding filaments? These questions matter enormously for calculating its effect on cosmological measurements but they are questions about the details of a real structure, not questions about whether the structure exists. Getting those quantitative details right is the work now in progress. Survey by survey, measurement by measurement, the void's properties are being characterized with increasing precision. The universe we inhabit, strange and surprising and emptier than we expected, is coming into clearer focus, one measurement at a time, from inside the cosmic hole we call home.